Next, we're going to cover the analysis domain of the exam, and this too covers a lot of subject matter. We'll start with Kinesis Analytics, which allows you to analyze streams of data in real time, and you'll build a hands-on example that analyzes streams of order data and alerts you on your cell phone when a sudden surge occurs. We'll then touch on Amazon's Elasticsearch service. Elasticsearch isn't just for search, it's a full-blown analysis engine that's often used for log analysis and visualization. We'll go hands-on with it as well, and analyze some real-world server logs using it together. From there, we'll cover Amazon Athena, which is AWS's serverless solution for querying massive data lakes stored in S3. Expect yet another hands-on activity there, where we will query our order data in S3 using Athena and the Glue data catalog. We're going to spend a lot of time on Redshift, which is AWS's data warehousing solution. Data warehousing is a big application of big data, and you will be expected to have a lot of depth on Redshift for the exam. For your hands-on activity there, you'll use Redshift Spectrum to treat our S3-based order data as just another table in our Redshift data warehouse. We'll wrap up with a discussion of the AWS Relational Database Service, or RDS, and how it fits into the world of big data. So let's get started and learn how to analyze your big data in AWS. As we start our journey into the analysis domain of big data, let's start off with Kinesis Analytics. It's another system for querying streams of data continuously, very similar in spirit to Spark Streaming, but it is specific to AWS Kinesis. So conceptually, it's pretty simple. Kinesis Data Analytics can basically receive data from either a Kinesis data stream or from a Kinesis data firehose stream. And just like Spark Streaming, you can set up windows of time that you can look back on and aggregate and analyze data across. So it's always receiving this never-ending stream of data, and you can just write straight up SQL to analyze that data and turn around and spit out the results to some other stream, which ultimately might go to some analytics tools of your choice. If we want to go into more depth, there are basically three main parts to Kinesis Analytics. One is the source or input data, and this is where the data to be streamed is coming from. Now the input or the source can either be Kinesis streams or firehose streams coming in from the left there, and that goes into our input streams. You can also optionally configure a reference data source to enrich your input data stream within the application. This will result in an in-application reference table. Maybe it's some sort of lookup data that you have that you want to refer to within your SQL of your actual analytics job. So if you want to do that, you have to store your reference data as an object in an S3 bucket. And then when your Kinesis Analytics application starts, the Amazon Kinesis Data Analytics will read the Amazon S3 object and create an in-application table so you can refer to that data in S3 however you wish. Then we have the real-time analytics, or the application code itself, sitting in the middle there. That's where the actual analysis happens, and that's going to perform real-time analytics just using straight-up SQL queries on your stream of information. So the stuff that forms the analytics job is called the application code. These are just SQL statements which would be processed on the streaming data and reference tables. And again, it can operate over windows of time, so you can look back through some fixed time period as new data is being received. Then we have the destination going out to the output streams there to the right, and that's where the processed data will go. So once the data is processed, the output can be sent to either a Kinesis data stream again or to another data firehose stream. And from there, it can go off to wherever you want, like an S3 bucket or Amazon Redshift if you want to store that in a data warehouse. Lambda might be involved too if you want to use that as the glue between these services to do whatever you want. Also, if any errors are encountered, those are sent out to the error stream. So Kinesis Data Analytics will automatically provide an in-application error stream for every application. If your application has any issues while processing certain records, like a type mismatch or late arrival, that record will be written out to the error stream for you. And I do want to emphasize how cool reference tables are. So if you're looking for a really inexpensive way to join data in for quick lookups within your Kinesis Analytics job, reference tables are a great way to do it. Again, all you need to do is store a mapping file in S3, which is really, really inexpensive, right? And if you can make that available as a reference table to Kinesis Data Analytics, you can just use a join command to join that data in from S3. So if you're not familiar with SQL, join is a way of combining data from two different tables. So for example, let's say you have one table that just has zip codes, but you want to actually look up the city associated with a given zip code. You might have a reference table that actually associates zip codes with cities, and then you can use a join command in SQL to actually join that data in and add that data to your output. So remember, If you need an inexpensive way of doing joins in Kinesis Data Analytics, a reference table is a great way to do it. Also, Kinesis Data Analytics now integrates with Lambda, so AWS Lambda can also be a destination for Kinesis Data Analytics. This gives you a lot of flexibility in how you do your post-processing on your data analytics queries. So you can do things like aggregate rows together, translate your data to a different format, transform the data, enrich it with additional data, or even encrypt that data through an AWS Lambda function that operates on the output from Kinesis Data Analytics. Also, by using Lambda, it opens up access to a lot of other services and destinations, so Lambda itself can talk to a lot of other things as well, including S3, DynamoDB, Aurora Redshift, SNS, SQS, or CloudWatch. So by sending your output from Kinesis Data Analytics to Lambda, that opens up a world of whatever you want to do in a Lambda function. So if you can write code for it and it can run in a short function, you can probably do it using Kinesis Data Analytics with Lambda. Also, we should talk about Kinesis Data Analytics for Apache Flink. Formerly, this was called Kinesis Data Analytics for Java, but under the hood, it's always used Flink, and Flink actually supports Scala as well as Java, so calling it Kinesis Data Analytics for Java wasn't really the right thing, because it can also support Scala. So they're more specific now. They call it Kinesis Data Analytics for Apache Flink. And Apache Flink is just a framework for processing data streams. And we don't have to go into too much detail about how Flink works, just know that it's an open source framework for handling data streams, and through Kinesis Data Analytics for Apache Flink, you can actually integrate an Apache Flink application that you developed yourself offline locally into Kinesis Data Analytics and use that Flink application to transform or somehow process data coming in through Kinesis. So instead of using SQL like we've been talking about before, you can actually develop your own Flink application from scratch. And what you do is you then load that application into S3. And when you set up Kinesis Data Analytics for Apache Flink, you just tell it where that code lives in S3, and it imports it into the Kinesis flow for you. And the advantage of this is that it is serverless, so you don't have to worry about where your Flink application is being hosted from or how it scales up and things like that. So let's look at a diagram here. Conceptually, Flink starts with something we call sources. And sources are what they sound like, where your data is coming from. And in Kinesis Data Analytics for Flink, you can have a Kinesis data stream, or you can also have Amazon MSK, managed streaming for Apache Kafka, as a valid Flink source. Those then get processed by your application. Again, you just dump your application in S3, tell Kinesis where it is, and it can run that as an Amazon Kinesis Data Analytics job. So the Flink application itself uses an API called DataStream. And the DataStream API allows you to talk to sources, operate on those sources, and then output them to what we call sinks. And supported sinks in KDA for Apache Flink include Amazon S3, Amazon Kinesis Data Streams, and Amazon Kinesis Data Firehose. So that's Kinesis Data Analytics for Apache Flink in a nutshell. Just remember that it allows you to import your own homegrown Flink applications into Kinesis Data Analytics using the DataStream API. You can connect to Flink sources that include Kinesis Data Streams or MSK, and output it to sinks that include S3, Data Streams, or Kinesis Firehose. What are some common use cases of Kinesis Analytics? Well, here's 3 of them. One is streaming, extract, transform, and load, or ETL. For example, you could build an application that continuously reads IoT sensor data stored in a Kinesis data stream, organize that data by the sensor type, remove duplicate data, normalize the data per a specified schema, and then go on to deliver that processed data to Amazon S3. Another example is continuous metric generation. So one example is you could build a live leaderboard for a mobile game by computing the top players every minute and then sending that on to Amazon DynamoDB. Or you could check the traffic to your website by calculating the number of unique website visitors every 5 minutes or so, and then sending the processed results off to Amazon Redshift for further analysis. Responsive analytics is another one. So an example of that would be an application computing the availability or success rate of a customer-facing API over time, and then sending those results on to Amazon CloudWatch. You could build another application to look for events that meet certain criteria and then automatically notify the right customers using Kinesis Data Streams and Amazon Simple Notification Service, or SNS. Let's talk about Kinesis Analytics' cost model. It is serverless, so you just pay for the resources you consume and nothing else. It scales up for you automatically, and you don't have to worry about the underlying resources needed to actually run your Kinesis Analytics applications. However, it's not cheap, unlike some other serverless services that AWS offers. When I was making this course, Kinesis Analytics actually made up the bulk of the actual charges that I incurred while developing this course. So use it carefully, and do make sure to shut down any analytics jobs once you're done using them, just to be safe. As far as security goes, you can use IAM permissions to access the streaming source and destination services that you're working with. So you can configure IAM to allow your Kinesis Analytics application to talk to whatever upstream and downstream services it needs to communicate to. There's also a cool feature in Kinesis Analytics called schema discovery. And that's how the column names in your SQL are found. It can actually analyze the incoming data from your stream as you're setting it up, so you can check that it worked. We'll see that in practice as we go into our hands-on exercise, but it's pretty cool. It can actually analyze an incoming stream, and right in the AWS console, you can see how it's trying to make sense of that data and impart a schema on top of it, and you can edit and correct that data as needed. It's also worth talking about something called random cut forest. This is a SQL function offered by Kinesis Data Analytics that you can use within your data analytics application for anomaly detection on any numeric columns in a stream. And you can tell that AWS is really proud of this because they published a whole paper on it. You can go look it up if you want to. It is a novel way of identifying outliers in a data set, so you can handle them however you need to. An example of doing this that they give in the paper is detecting anomalous subway ridership during the New York City Marathon. So they have a stream of data of people going through the subway turnstiles, and they are using random cut forest to automatically identify anomalies in that rate of usage of the subway system. So this is important because if you ever see a question about trying to detect anomalies or outliers in a stream of data, random cut forest with Kinesis Analytics is very likely a good answer for that. And with that, let's dive into a hands-on example because it will make a whole lot more sense when you see this all in action. All right, let's build our next activity here, the transaction rate alarm. This is a fairly complicated one, so let's study this diagram a little bit. So at a high level, what we're trying to do here is build a system that will monitor the incoming orders from our server logs that we're going to generate on our EC2 instance and send out an alarm actually to my cell phone in the event that we get more than, say, 10 orders per 10-second period. That might indicate that somebody's throwing some sort of inordinate amount of traffic at us. Maybe it's malicious, maybe it's some sudden surge that we weren't anticipating, but either way, it's something we want to know about. So the way this will work, we'll start by piping those order logs from EC2 using the Kinesis agent into a Kinesis data stream. And that's going to be the same Cadabra orders stream that we set up earlier. From there, we're going to use Amazon Kinesis Data Analytics, and that's really the heart of this exercise and activity to illustrate the use of that. And we're going to be using some of the newer features of Kinesis Data Analytics. We're going to be using its integration with Apache Flink, and we'll be doing that using an Amazon Kinesis Data Studio notebook, which is kind of a cool new thing. From there, we're going to pipe the outgoing counts of number of orders per time period into another Kinesis data stream. We're going to call this one order rate alarms. And from there, we'll land into an AWS Lambda function that will analyze the incoming order counts and, if appropriate, fire off a notification through SNS to your cell phone. So pretty neat stuff. A whole end-to-end system here where we're monitoring orders coming in from our server logs in EC2 into a Kinesis data stream. Data analytics will monitor that stream in real time, send the order counts to another data stream, which will then in turn be looked at by a Lambda function, which in turn will talk to SNS. The reason we have Lambda in the middle there is a couple of reasons. One is to give us more flexibility in how we process this data. Maybe I want to add some logic later on to make sure that I suppress alarms while I'm in an alarm state so I don't keep setting the same alarm repeatedly. And it also allows me to talk to SNS because I can't talk to SNS directly from Kinesis data streams. So let's dive in and see how it all fits together. All right, I've already signed into my AWS Management Console, so if you are following along, go ahead and do the same. Let's start by creating our Kinesis data streams that we need. So let's go ahead and go to Kinesis, either through here or you can search in the search bar here. And if you did delete the Cadabra order stream previously to save money, you'll want to recreate that now. So let's start by doing that. We'll just hit Create Data Stream, and we'll call it Cadabra Orders. Really easy to mistype that, so pay attention to spelling there. And one shard will be enough for our little test environment. Let's go ahead and create that stream. And while we're at it, let's create a second stream as well. And while we're at it, let's set up a second stream as well. Go back to data streams and create another data stream. So this will be the stream that actually goes out from data analytics into Lambda with the order count information over time. We're going to call this one order rate alarms. All right, again, one shard is more than enough. All right, so now let's fire up our EC2 instance that we'll be using to generate the logs. So back to services, let's find our way to EC2. And start up your EC2 instance that you're using for this course. For me, it's called AWS Data Analytics. Yours is probably called something else. Instance state and start instance, and we just wait for that to spin up. And I'm going to go ahead and pause this video while we wait for that to activate. So go ahead and hit pause yourself and resume once your EC2 instance is ready to go. All right, looks like my instance is now running. So let's go ahead and make sure that's still selected and hit the connect button. And to make life easy, I'll just use EC2 Instance Connect and connect over my web browser. And we're in. All right, so you should still have Kinesis and the Kinesis agent installed from the previous activities. If not, go on back in time and do some of the earlier lectures to get that set up, but hopefully you still have this all in place. Let's just double check the configuration though. So let's go to sudo nano /etc /aws-kinesis /agent.json, just like that. And your config file, agent.json, should look something like this. So first of all, make sure that kinesis.endpoint is set to your appropriate endpoint. Again, for you, that might be different. For me, it's US East 1, but you may need to substitute US East 1 with the region that your account is set up in. If you're not sure, just go back to the AWS dashboard and click on this little thing here, and whatever is highlighted there as your region should have the region name next to it. So again, for me, it's US East 1. For you, it might be something else. But whatever it is, make sure that you insert it within your endpoint here for kinesis.endpoint. All right. And now down in the flows, you want it to look like this. So you may have removed the Cadabra orders stream before. If so, go ahead and replace it to match what is shown in this screen here. So make sure the file pattern is set to /var/log/cadabra/star.log. That's where our little script that generates fake data will put that stuff. The Kinesis stream name is Cadabra orders that we created earlier. Partition key option will be random. And make sure these data processing options are set up as shown. And pay attention to the brackets. So we have a square bracket here, curly bracket there, and a pair of square brackets in the custom field names. So we're setting this up to convert from CSV data to JSON data on the client side here. And we're going to be feeding JSON data into our Kinesis stream that contains fields for invoice number, stock code description, quantity, invoice date, unit price, customer, and country, just like this. So take a moment and make sure that your file looks like this. Again, the only difference should potentially be the region in the endpoints above. So hit pause and make sure that that's okay. When you're ready, hit resume. All right, let's go ahead and write this out. So if you did make any changes here, you can just say Control O to write them out, and then Control X to exit. And I'm back at my command line here. Alrighty, so let's go ahead and restart the agent to make sure that it's going to pick up any new logs that I add in there. So to do that, we'll say sudo service aws-kinesis-agent restart. And give that a moment to complete. All right. So we have EC2 ready to send logs to our stream. We have our streams ready to go. I want to do the actual Kinesis data analytics stuff last though. So let's skip ahead to the Lambda function and the SNS topic that we're going to publish to next. And once we have all the components in place that we need to refer to, we'll come back and take care of the Kinesis data analytics part in the middle. All right, moving on, let's go ahead and set up our SNS topic next that will actually be responsible for sending text message alarms to your cell phone. So back to the AWS console here, and let's switch to SNS. Again, there's many ways to get there. Let's go ahead and just search for it up here. So let's start by creating a new topic. We'll select topics in the dashboard here and say create topic. So we do want to change the type to standard because we do want to be sending out SMS messages and not just SQS. And we'll go ahead and give it a name. Let's call it Cadabra Alarms and give it a display name of Cadabra. So the display name is just the thing that will be displayed in the beginning of our SMS messages to identify it as coming from this system. All right, I think that's all we really need here. We don't really need to encrypt this stuff. We're not sending anything sensitive. The default access policy should be fine. Default retry policies should be fine. 3 retries maximum. And delivery status logging, I don't really care for what we're doing. And I don't need any tags. So let's go ahead and hit create topic. And our topic has been created. All right, up next we need a subscription to actually do something when this alarm gets fired. So let's go ahead and hit subscriptions and say create subscription. Now this message at the top is important if you live in the United States. So effective June 1st, 2021, you can't just send anonymous text messages around. You have to have an actual phone number or some sort of identifier behind it identifying where it came from. This is presumably to combat text message spam. So if you do want this to actually go to a US phone number, you're going to have to set up an 800 number behind it. So if you click on view origination numbers, like it says, you can see I've already set one up. It only costs $2 a month. So, if you are comfortable with spending $2 a month for this service, go ahead and provision a number. And you can do that by just hitting the provision numbers and pinpoint button here. And it kind of walks you through what you need to do. So what you want to do is actually request a phone number. And from there, it should be pretty obvious what you need to do. Select your country. You want a toll-free number. And you only want SMS capability. Again, you only need to do this in the United States. You can see this will cost you $2 per month. I've already done this, so I'm not going to hit next, but if you did want to go through with this, go ahead and hit next. You don't have to, even if you're in the United States. You will see in the dashboard here that it attempted to send the text message at least. So you're paying that $2 just to get the satisfaction of actually seeing your phone do something at the end of this exercise. But again, totally optional. Let's go ahead and find our way back to... So let's find our way back to that subscription we were trying to create. Actually, let's do that by going back to the topic. And from there, we can make sure that the right topic name is set up for it. So back to services and SNS. And let's go to topics this time. Select the topic we just created, Cadabra Alarms. And from here, click Create Subscription. All right, so now the topic ARN is filled in for us automatically. Protocol should be SMS, simple message service. That will send text messages. We need an endpoint to send it to, so just put in whatever your cell phone number is to receive these messages. I'm going to blur that out so nobody gives me any prank calls. And go ahead and click on Create Subscription. All right. Let's go back to our topic, Cadabra Alarms, and publish a message to it and see what happens. We'll just give it a subject, testing, and a message body. This is only a test. And we don't need any attributes. Let's go ahead and hit publish message. And if we're lucky, my phone will make a noise. Let me turn up the ringer on my phone so we can see if it actually works. It did. My phone buzzed. Yay. So I am looking at a text message on my phone right now that says Cadabra. This is only a test. So awesome. It works. All right, SNS is set up. The next step is going to be Lambda. So that's going to be the glue between Kinesis Data Analytics and this SNS alarm. So let's go back to Services and select Lambda. And we're going to create a new function. It dumped me into applications by default, but I don't want an application. I want a function. So let's switch to functions. And create function. We're going to author this from scratch. Let's give it a name. We'll call it Transaction Rate Alarm. And I'm a Python guy, so I'm going to change the runtime to Python. 3.9. Wow, getting up there. All right, we do need the execution role. And we're going to create a special role that has permission to SNS and Kinesis. So let's go ahead and hit the link to the IAM console here and create a new role from scratch. Let's go ahead and select Lambda as the use case. And we will add the following permissions. So we need AWS Lambda Kinesis execution role. Go ahead and select that. We also need Amazon SNS full access. Select that. And we need AWS Lambda basic execution role. Select that. And that, oh, we also need CloudWatch. So CloudWatch logs full access. There it is. And I think that's everything. Let's move on to the tags. Don't need any. And review what we have. We need to give our role a name. Let's call it Lambda Kinesis SNS. Don't care about the description right now. Just make sure we have the right policies attached. AWS Lambda Kinesis execution role, Amazon SNS full access, CloudWatch logs full access, and AWS Lambda basic execution role. Let's go ahead and create that role. And it's been created. So now if I go back to my Lambda dashboard here, I should be able to say use an existing role, and hopefully it will show up. There it is, Lambda Kinesis SNS. We'll select that. Check the advanced settings, make sure there's nothing we care about. Code signing, network access. No, don't need any of that. Go ahead and create the function. All right, the console here got a little bit confused because I made this function earlier, but I think I cleared it all out for you here, starting from scratch here. First thing we'll do is add a trigger. So we can actually have our Kinesis stream trigger this function and do something with it. So we'll say select trigger and select Kinesis, wherever it is. There we are. And we'll select the stream that we're listening to. This is going to be the output stream from Kinesis Data Analytics, so that's going to be order rate alarms. Let's just double check the settings here. All looks reasonable to me. Go ahead and hit add. And let's make sure the timeout for this function isn't too small. So under configuration, let's go to general configuration. 3 seconds is probably not enough. Let's change that to 1 minute. Just to be safe. All right, now we need some code. Go ahead and click on the Code tab. And to make life easy for you, I've put a copy of what you need into the course materials. So let's go ahead and open that up. So under the course materials, head into transaction rate alarm, and from here there's a lambda.txt file with a handy dandy cheat sheet you can copy from. So Control A to copy all that, Control C. And let's go ahead and highlight all this existing code and Control V to paste it in. Now you'll see there is a placeholder here for your SNS topic ARN. So we need to tie this to SNS when it receives data. Let's just quickly talk about what's happening here. So our Lambda function is just sitting there waiting for stuff to come in. Again, it's triggered by that Kinesis stream. So once it sees stuff coming in from that order alarm stream that's coming out of Kinesis Data Analytics, it's just going to go ahead and fire off an SNS message. So you can see here we're creating an SNS client through Boto 3. We're going to set our topic ARN in a moment here. The actual code will just say publish on SNS with the given topic ARN with a message that says, hey, investigate sudden surge in orders and a subject of Cadabra order rate alarm. And it will either successfully deliver that or it won't. And that's all there is to it. Obviously, you could be much more fancy here. For example, I could keep track of whether I'm currently in an alarm state by writing that out to DynamoDB or something, and that way I can make sure that I'm not repeatedly sending text messages while we're in a bad state, that it will actually just stop sending them until things go back to normal and when things get bad again. So I will leave that as an exercise for the reader. That has nothing to do with data analytics, so I'm not going to get into it now and further complicate matters. This will work for now for our testing purposes. But we do need that SNS topic ARN, so let's go to another tab here, the one that we were using for IAM before, and go ahead and switch back to SNS. Simple notification service. Let's find that topic that we just created, Cadabra alarms, and there's the ARN for it. Just go ahead and copy that. And I'm going to paste that into my Lambda code. So where it says your topic here, I'm going to paste my topic name. Make sure you don't have any you didn't lose the quotes or you don't have an extra quote or something. Easy to mess that up. Should look something like that. Go ahead and hit deploy to deploy those changes. All right, so at this point, we have our EC2 instance ready to publish logs into our Kinesis stream. We have another Kinesis stream ready to receive information from data analytics that will go into our Lambda function that we're looking at here, which in turn will go to SNS. The only piece left is the heart of the whole thing, Kinesis Data Analytics, which will tie it all together. So let's do that next. So let's go ahead and use Kinesis Data Analytics to monitor our incoming log data and output alarms when there's more than we expect. So I'm back to the Kinesis dashboard here. Let's select Analytics Applications and select Studio, because we're going to actually use a notebook for this. So let's go ahead and create a Studio notebook. And we need to use custom settings because we actually have a destination where we're sending stuff to, and we want to make sure that we have all the right permissions necessary for that automatically. So we'll select Create with Custom Settings. We need to give it a name. Let's call it, I don't know, Transaction Rate Monitor. Latest Flink, latest Apache Zeppelin, that's fine. Hit Next. Now the Kinesis Studio needs a glue database to work with to store all of its schemas in and whatnot. So we're going to just create an empty database here for it to work with. So I'm going to hit Create. That'll bring me off to Glue. And we'll add a database. Let's call it Transaction Rate Alarm. And that's it, just a dummy empty database. Let's go back to Kinesis Analytics, refresh that list, and we should see it. Transaction Rate Alarm. All right, our source is going to be the Cadabra orders stream, right? So let's hit Choose Source and browse for the Cadabra orders stream. Choose that. Save changes. And for the destination, same deal, choose destination. Browse, and that's going to go out to the order rate alarm stream that ties into Lambda. Choose that and save changes. Okay, so that should automatically set up what we need in the IAM policy for this. Let's hit Next. Definitely don't need more scaling than that, so let's go ahead and leave the defaults. Logging, fine, can't hurt. And all the defaults for networking should be fine. And we don't need any of these optional connectors either. So let's go hit Next again. Review everything. Looks good to me. And scroll down to the bottom and create Studio Notebook. All right, now before we can use it, we need to run it. And once you hit run, the hourly charges start racking up. So make sure you shut this down when you're done. That will take a minute or two to start up, so I'm going to go ahead and pause until that's ready. All right, our notebook is ready to go, so I'm going to go ahead and click on Open in Apache Zeppelin. And what we'll get here is a notebook environment. So let's go ahead and to make your life easy, I'm going to let you import a note in your course material. So let's click on Import Note. And we'll give it a name, Transaction Alarm, whatever you want to call it. And we will select our JSON file. and navigate to your course materials folder. Under transaction rate alarm, there should be an examples.zpln file. So let's go ahead and open that up and check it out. So what we have here is a notebook environment that allows us to use Apache Flink, and Flink in turn integrates with Kinesis. So through Flink, we can receive data from Kinesis data streams, transform them in any way that we want using SQL commands, and then output the result to another stream, which is exactly what we want to do. So the first thing we need to do is create a table within Flink for receiving data from the Cadabra orders stream. So this is going to be what's coming in from those order logs in JSON format from our EC2 instance. So that's what's going on in this block here. We're going to create a new table called orders JSON, and it's going to have this schema. So we need to explicitly give it a schema. It has an invoice number, a stock code, description, quantity, invoice date, unit price, customer, country, and we'll talk about arrival time separately. These are all going to be strings for now of a given length. Obviously, some of these are intended to be numeric, but because we haven't really done anything to clean our data yet, we don't want to be dealing with any errors as a result of misformatted information getting inserted into that table. So just to keep things simple for now, we're going to keep these all as string data types. In the real world, however, you'd want to set up some sort of pre-processing of that data to clean it and make sure it's in the format that you intend. The final column in our table is arrival time, and this is a special one. We're going to say arrival time as proc time. What this does is tell Flink that I want to take the time that this data was processed, the time it was actually received, and put that timestamp into a new column called arrival time automatically. So arrival time is not in our incoming JSON data, but we're going to say we want to automatically insert that for the processing time of this data as it comes in. Now we need to tie that table to Kinesis, and that's what this with block does. It says we're using the Kinesis connector. It gives it the name of the stream, Cadabra orders, the region. Again, for you, this might be different. For me, it's US East 1. For you, it could be something else. Again, if you're not sure, just go back to your AWS dashboard, click on the region here, and it will show you the region that you're in. And finally, we say that it's in JSON format. We're going to use the latest version, the latest data as it comes in as a starting position. And the format of timestamps is ISO 8601, just standard stuff there. So let's go ahead and run that and see if it works. So a few ways of doing that. I could hit the play button here or just hit Shift Enter. I'll hit Shift Enter. And it'll take a moment for Flink to spin up and all. All right, our table has successfully been created. Cool. So note this first line here. I kind of skipped over that. It says %flink.ssql. What this is doing is telling the notebook that I'm running a Flink environment here, and SSQL means that I'm just running this in batch mode. Okay, so it's just saying that I'm going to be feeding SQL commands into Flink within this block. Now, in contrast, this next block here is different. It says type equals update. So that means that I want this block to actually run continuously. It's going to be monitoring that streaming data and updating the output over time as new data is received. So a little bit different there. That's what type update means. It means it's going to keep on running this forever until I abort it. And all we're going to do is select every column from the orders JSON table that we just created. So by running this, and I'm going to go ahead and do that, Shift Enter, that's going to be monitoring the orders JSON table, which is tied to my Kinesis stream, right? So as new data comes into my stream, I should see it showing up here. So this is just a test to make sure that everything's connected. Right now, I don't have any data in my stream. I haven't published anything to it yet, but you can see that it did pick up the schema that I defined earlier, so that looks good. So let's feed some data into that stream and see what happens. So let's go back to our EC2 console here. I'm pretty sure this is probably timed out by now. Yeah, but if I refresh this, it should come back to life. Yep, cool. So let's go ahead and pump some data into it. And to do that, we're going to make sure we're in our home directory. CD tilde if you're not sure. And you should have already downloaded the loggenerator.py script and its associated data. Let's go ahead and say sudo./loggenerator.py, and by default, that should write 100 lines into the stream. Let's monitor its progress to be sure. tail-f/var/log/AWS Kinesis agent /AWS Kinesis agent.log. And you can see that it's already parsed those 100 records. It hasn't actually tried to send it off yet, though. But let's switch back to our notebook here and see what happens. It does take a minute for that to get through. Just going to keep kind of flipping back and forth between these two screens here. Still, it hasn't been sent to the destination yet. 100 parsed, but 0 sent. Kind of wait for that to go through. But pretty soon we should see data flowing through here. And there it is. Cool. So while I wasn't looking, some data streamed in, and you can see here it looks legit. So we have invoice numbers and stock codes and descriptions and quantities and invoice dates and unit prices, and most importantly, that arrival time column of when that data was actually received. So now we can pay attention to that arrival time to figure out how many orders am I receiving in a given time interval, right? So this is the whole idea of streaming data. We're going to be looking at the data over some window of time and analyzing it over that window. Let's go ahead and cancel this now that we know that it's working. Just hit the pause button to abort. So let's go ahead and try to analyze this over a window of time. That's what this next block is doing. So here, again, we're doing type equals update. We want this to run continuously until I stop it. And it's going to select star from, select cast count star as integer as order count. So I'm sort of building up a command here that will insert this into the output stream. That's why I'm doing this sort of nested select statement here. But at its heart, we have a select count star as order count. So we're taking the total number of rows that have been received and calling that a new order count column that's going to be put into a new table, right? We're going to be doing that from the orders underscore JSON data that's coming in. So that's our streaming input data of orders information. Group by, and this is the heart of it all, tumble, arrival time, interval 10 second. What does that mean? That means that every 10 seconds, we're going to just look at the information within that 10-second interval. And we're going to be basing that time on what's in the arrival time column that we inserted, the processing time. So every 10 seconds, we're going to look over the previous 10 seconds and say, how many orders did I receive? And it will output that number as order count. That's all that's happening here. Pretty straightforward SQL here. The only thing that's special about it is this tumble command, which allows us to apply it to a streaming window. Now, tumble is only one way of doing it. There's also a hop command that lets you do more of a traditional sliding window that you might see in streaming applications. So if you needed to do a sliding window where you had an interval time that was separate from the window time, you could do that with a hop command. But again, I'm keeping it simple. We're just going to use tumble and say if I ever have more than a certain amount of orders within a 10-second interval, I'm going to fire off my alarm. So let's just make sure this works. Let's go ahead and hit Shift-Enter. And again, we'll kick off some more data. So back to my console. Control-C to stop that log tail. And I'm going to hit the up arrow a couple of times to go back to sudo loggenerator.py and write out another 100 lines of data. Up arrow a couple of times to get back to my tail command so we can monitor what's going on. And we'll head on back to our transaction rate monitor notebook here. And you can see here that all that I'm outputting now is that order count column that I've created. So that will be spitting out the total number of orders received every 10 seconds as data comes in. So once we get that burst of streaming data from the EC2 client, we should see those 100 orders come through here. And again, it takes a minute for that to go through. We can see the next 100 records have already been parsed. We're up to 200 now, but only 100 have been sent so far. It's working on sending it into the stream now. So pretty soon we should see that showing up here. There it is. So we can see during a 10-second interval, we received 100 orders. Okay, so it looks like that's working. Very cool. And another 10 seconds have gone by the way, and we're seeing nothing because no new orders have been put into the stream. So cool, that worked. Let's go ahead and cancel that block. And let's put it all together. So finally, we need to actually put this into our output stream, right? So that's what this block does. It actually creates a table tied to our output stream. We're going to call it order count table. And it just contains that one column, order count of an integer. And the with block just defines how it's tied to Kinesis. Again, we're using the Kinesis connector. The stream that we're going to be writing to is order rate alarms. The region for me is US East 1. Again, change that if you need to for your region. Again, the initial position will be the latest. The format is JSON, and the timestamp is ISO 8601. So let's go ahead and Shift Enter to create that table that ties into Kinesis's order rate alarms stream. And finally, we'll tie it all together. Again, we're going to do an update here block with Flink SQL. So continuously, we're going to be running that same little snippet of code that monitors the orders JSON. That's going to be monitoring the incoming Cadabra orders Kinesis data stream. It's going to be adding up how many orders are received over every 10-second window, and it's going to output that value into the order count table, which in turn is tied to the order rate alarm stream. And we're only going to do this where the order count is greater or equal to 10. So the way we've set this up is that if I'm receiving more than 10 orders per 10 seconds, I'm going to consider that unusual enough behavior that I want to wake somebody up and send a text message to them on their cell phone. And that's exactly what should happen now. So let's go ahead and Shift Enter to kick that off. So now this should tie everything together, right? So as I kick off more data here, let's go back to EC2, Control C on my tail, up, up, kick off another 100 lines, up, up to tail it, and back to the monitor. So what we should see happen now is as that data is received, we already know that that stream is going through to Kinesis Data Analytics. Once it sees that burst of 100 orders come through, this should trigger because the order count will be more than 10, and that should dump it into the order rate alarms data stream. And that order rate alarms data stream should in turn go to our Lambda function, which in turn will fire off our SNS alarm. So let's wait and see what happens. There's no actual output here. I'm just going to wait for an actual text to come through on my phone. And I just got it. That's awesome. So I can see here in the tail that that data just got processed. And as I was looking at it, my phone went off. How cool is that? And again, there's no output that we set up here to happen in that case. But yeah, I got a text message right now that says Cadabra, investigate sudden surge in orders. So it worked. How cool is that? So we have successfully built an end-to-end system here with Kinesis Data Analytics at its core, and also illustrated use of the Kinesis Studio notebook feature that's new. There are other ways of doing this. You can build a standalone application outside of a notebook as well. That's still an option. In the old days, you would have done this just using plain old SQL without Flink. That's not really supported anymore, though. So Flink is the way to go these days. So for prototyping, a notebook is a very handy environment for experimenting, seeing what works. You could later on put this into a standalone Flink application instead. But there you have it, Kinesis Data Analytics tied to Flink in a notebook, using Kinesis data streams and tying that into Lambda and SNS for a functional system that alarms when I get too many orders. Pretty cool. Let's remember to clean up our mess, though. We'll do that in the next lecture. All right, let's clean up our mess so we don't get billed for stuff that we're not using. Let's start by closing out this notebook here. And back to Kinesis Analytics here. Let's select our streaming applications. Select the Studio tab, select our Transaction Rate Monitor notebook, and we're going to stop that first. Wait for that to stop. Your notebook does bill you by the hour, so you want to make sure you don't leave that running if you're not using it. Can take a couple of minutes, so I'm going to come back when that's done. All right, it stopped, so now I can delete it. Actions delete. And we'll confirm that. All right, so that's getting deleted. Also important to delete our data streams because those are also charged. Not a whole lot, but you do get charged by the hour whether those are being used or not. So let's go back to Kinesis and select data streams. Select both of our streams and delete them as well. Let's also go to SNS and delete our subscription. and the topic it was tied to. And if we had a phone number set up for this, we need to get rid of that too. So we need to go to Pinpoint to do that. Let's go to the Pinpoint console. And we should be able to select that phone number and say remove phone number so we don't get billed for it every month. Should also get rid of that Lambda function. So let's go back to Lambda. Transaction rate alarm. Let's delete that. And all that's left at this point is the glue database. You can get rid of that if you want to. And there was the IAM role that we created for our Lambda function. Not doing any harm, but if you want to get rid of that, you can. All right, and let's not forget our EC2 instance. Let's go back to our console here, Control C to stop it and exit out of that console. Close that window out. And let's go back to EC2. And select my instance here and stop it. All right, so that should take care of everything that we might be getting billed for, which is what's important. So now that we've cleaned up our mess, let's reflect again on what we've accomplished here. We built a pretty cool application. It actually monitors logs coming from a real EC2 instance going into Kinesis data streams. We built a Kinesis data analytics application using the new Kinesis Studio and Apache Flink. And that tied to another Kinesis data stream that talked to Lambda, which talked to SNS, which sent an actual message to my real cell phone. So cool, fun stuff. All right. Hope that drove home how to use Kinesis data analytics in the wild, at least in the new studio environment. That might be something you see. And again, remember that it is possible to create a data analytics application outside of the studio as well. I'll show that to you real quick here, just to give you a pointer. Let's go back to Kinesis analytics application. If I were just to hit create application here, it would actually prompt us to create a new Flink configuration and to upload the actual Flink code that we want to run. So again, the Studio Notebook is a good way to sort of prototype things, but if you wanted to actually do this in production, you might use this process instead. There you have it. So let's dive into Amazon's OpenSearch service, which was formerly known as Amazon's Elasticsearch service. We'll get into the history there shortly. But it's a pretty exciting technology for doing large-scale analysis and reporting at petabyte scale. And what's interesting is that even though OpenSearch, formerly Elasticsearch, started off as a search engine, that's fundamentally what it was made for originally, it's not just for search anymore. Really, it's primarily for analysis and reporting these days. And for some applications, they can actually analyze massive data sets like that a lot faster than something like Apache Spark could. So for the right sorts of queries, OpenSearch can be a really good choice for getting answers back really quickly across a massive data set that could span petabytes across an entire cluster. So let's dive into what it's all about. So what is OpenSearch? Well, let's get into the drama here. So OpenSearch is a fork of Elasticsearch and Kibana. So there's a little bit of drama here. Basically, there was a licensing dispute between Elastic and Amazon. So originally, Amazon was offering the Amazon Elasticsearch service, which was just the Elasticsearch product on their servers, basically. Elastic didn't really like them eating into their revenue this way, so they changed the license on Elasticsearch, which forced Amazon to make their own branch that they're maintaining themselves and calling OpenSearch. This all happened in September of 2021, so within the tail end of 2021, you'll probably continue to see this referred to as the Amazon Elasticsearch service on the exam and elsewhere. Now, they're calling Elasticsearch OpenSearch now, and Kibana was actually the visualization tool that was part of what we call the Elastic Stack. So Elasticsearch was part of a larger ecosystem from Elastic that included Elasticsearch, a visualization tool called Kibana, and also some data ingestion tools called Beats. But for OpenSearch, it's just a fork of Elasticsearch and Kibana. They're calling this OpenSearch and Dashboards now. But the main takeaway is that OpenSearch is fundamentally a search engine. So you can send it JSON style requests and say, go index this document. And another JSON request to say, go search for documents that contain these keywords or these attributes. Or you can do things like fuzzy matching and things like that as well. So at its heart, OpenSearch itself is a very good and scalable and very fast search engine. It's actually built on top of an open source solution called Lucene. So we have kind of these layers where Elasticsearch was built on top of Lucene, and then OpenSearch was branched from Elasticsearch. It's really convoluted, but that's how we got here. But fundamentally, OpenSearch is a scalable version of Lucene, and is distributed horizontally across many nodes in a cluster. However, it's been expanded over the years to include more and more tools and become more of an analysis and a visualization tool. So another piece of the OpenSearch package is called Dashboards, which is a branch of what they called Kibana in Elasticsearch. Confused yet? Right. Basically, it's a visualization tool for querying and analyzing and visualizing data that's stored in OpenSearch, so you don't have to limit yourself to storing document information in OpenSearch. I mean, you could use it to build a search engine for Wikipedia or something like that, but you can also use it to store semi-structured data, like data coming in from server logs or something like that. And if you're doing that, you could use dashboards to visualize that kind of data and make your own little Google Analytics dashboard, if you will, from scratch. It also serves as a data pipeline. So they realize there's a need to actually feed data at scale into Elasticsearch or OpenSearch now. And kind of like you can use technologies like Kinesis and Kafka to do that in other systems, within OpenSearch you would probably be using Kinesis to handle the ingestion of data from your servers into OpenSearch. Now, in the Elasticsearch world, they had technologies called Beats and Logstash that would do this for you as well. Certainly on the exam, you can expect them to talk about Kinesis integration with OpenSearch as opposed to Beats and Logstash integration because they're trying to get away from that whole world. But that's what OpenSearch is all about. Basically, it's Lucene scaled out infinitely as you add more servers to your cluster. So I promised you a closer look at dashboards, formerly Kibana. So here's an example of a dashboard just to give you sort of a gut level feel of what it's capable of. And as we said, you can easily import log data using Kinesis into an OpenSearch cluster and then use a dashboard to visualize that data. You can also use dashboards as sort of a nice to use front end or UI for actually querying that data interactively and trying out specific requests on your data set without having to type in command lines for using curl from a terminal or something like that. So this is what a dashboard looks like. Again, just think of it as sort of a Google Analytics dashboard for your data stored in OpenSearch. And it's a very scalable solution for that. So there are some companies that are either uncomfortable with exposing all of their data to Google, or their data is too large for Google Analytics to handle. So for them, dashboards and OpenSearch is actually a really good alternative to look into. So what is OpenSearch used for? Well, like I said, it's not just for search anymore, although that is still a really great application of it. If you do need to build a search engine for a website or something, Elasticsearch is a great tool for that. And it's also very scalable, so it's totally feasible to build something like search on Wikipedia using Elasticsearch. Or OpenSearch, rather. I'm still saying both of those words. They're the same thing right now. But it's also for other things too, like log analytics we talked about. It's very well suited for that. Also application monitoring based on incoming log data. It's a very quick and easy way to visualize what's happening in real time as your data comes in from monitoring your servers. Security analytics is also an application, and clickstream analytics. Really, this all falls under the umbrella of analyzing log data, though that's really kind of the niche that OpenSearch has started to fill. So to go into some specific examples, though, for full text search, MirrorWeb uses Amazon Elasticsearch or OpenSearch service now to make the UK government and UK Parliament's web archives searchable. And using the Amazon OpenSearch service, MirrorWeb indexes 1.4 billion documents, billion with a B, for just $337, and indexed 146 million documents per hour, which was 14 times faster than the previous technology they were using. So as you can probably tell, I'm talking about case studies that AWS gives you that I'm talking about here, where they talk about how awesome they are, but it actually is impressive how performant and cheap this can be. So for log analytics, Adobe uses Amazon's OpenSearch service as well, and they're visualizing large amounts of log data for its developer platform, and at peak, they're receiving over 200,000 API calls per second. I mean, that's pretty mind-boggling traffic right there, even for me. But using Amazon OpenSearch, Adobe can easily see traffic patterns and error rates and quickly identify and troubleshoot any potential issues, all with reduced operational overhead because Amazon's doing the server maintenance for them. For application monitoring in real time, Expedia is an example of a customer of Amazon. For that, they're using Amazon's OpenSearch service for application monitoring and root cause analysis and price optimization. And Amazon OpenSearch is enabling Expedia to monitor huge volumes of Docker logs cost effectively and identify and troubleshoot issues in real time and scale easily to accommodate additional log sources and offload the operational overhead as well, because again, it is a managed solution. In the realm of security analytics, Amazon OpenSearch allows you to centralize and analyze events from across your entire organization in real time. You can index and analyze your data as soon as it's received from multiple sources instantly and find and prevent threats faster. And finally, for clickstream analytics, the example they give is Hearst Corporation. They build a clickstream analytics platform using Amazon's OpenSearch service and Amazon Kinesis Streams and Amazon Kinesis Firehose. We'll talk about how those all fit together shortly, but it's built to transmit and process 30 terabytes of data a day from 300 plus Hearst websites worldwide. That's a lot of information. And with this platform, Hearst is able to make the entire data stream from website clicks to aggregated data available to editors within minutes. So it's massive scale, near real time, and it's cheap. Awesome stuff, right? Let's talk about OpenSearch's main concepts here. So basically, there are three different kinds of entities you need to think about in the context of OpenSearch. One is a document. So basically, OpenSearch is a document storage and retrieval engine. Documents are the things you're looking for, and it's not just limited to text. You can put structured JSON data in there as well. Now, every document is going to have some unique document ID that you can search for by. And currently, but not for much longer, also a type associated with it as well. Types are what would define the schema and mapping shared by documents that represent the same sort of a thing, like a log entry type or an encyclopedia articles type. Basically, it defines the schema you expect to see associated with that type of document. However, types are going away, and we're moving to just one type per index right now. And in later Elasticsearch releases and presumably later OpenSearch releases, they're going to be eliminated entirely. In fact, already on the new UI for OpenSearch, you'll see that the type field is grayed out because they don't even want you thinking about types anymore. So today we talk more about indices than types. An index would power search into all documents within a collection of types. An index also contains an inverted index that lets you search across everything within that index all at once. So in OpenSearch, we have one type per index. So the structure that's expected is that for any given type of document, you're going to have a specific separate index for that type. And ultimately, the entire concept of types is going away, and you can just put whatever data you want into your JSON data. So again, types are going to be a thing of the past soon. So you really just want to think about documents and indexes. But if you see something on the exam about Elasticsearch 6 still, types still might be a thing in that context, but I'm sure they'll be updating the exam soon if they haven't already to not talk about types. How does it all work? Well, an index, which again is a collection of documents that are related to something, is split into shards. So this is pretty much straightforward horizontal scaling stuff, right? Basically, every document is hashed to a particular shard, and every shard might live in a different node within a cluster somewhere. And what's interesting is that every shard in OpenSearch is actually a self-contained Lucene index of its own. So every shard is kind of its own little mini search engine. It's kind of cool. Now, redundancy works in much the way you would expect. So in this example, we have 2 primary shards and 2 replica shards for each primary. And the way it works is that write requests would be routed to your primary shard and then replicated to however many replicas you specify. Read requests, however, can come from either the primary or the replica shards, so it's up to your application, actually, to round robin that and try to distribute the load of those read requests so that you're not putting all of that load on the primary shard for reading. You can make use of those replica nodes for expanding your read throughput as well. Now, so far we've talked about what OpenSearch shares in common with Elasticsearch, their common fundamental architecture, but let's talk about what's specific to the Amazon OpenSearch service. All right, so the Amazon OpenSearch service is a fully managed service to make it easy to deploy, secure, and operate OpenSearch at scale with zero downtime. So before this, you would have had to install Elasticsearch yourself on a bunch of EC2 instances and manage that yourselves based on your requirements. But now you don't have to worry about all that. All the pain of managing those instances and installing patches and all that stuff is done by AWS, just like it would be on RDS or EMR. But it is not serverless, so you still have to decide how many servers you want in your OpenSearch cluster. That's not going to be scaled up and down for you. You still have to think about the actual servers in your cluster, kind of like with EMR. It offers the OpenSearch APIs, a managed dashboard, and integrations with Kinesis and other AWS services to enable you to securely put in data from any source and search and analyze and visualize that data in real time. You only pay for what you use. You pay for the instance hours used by your cluster, the storage actually consumed by it, and the data transfer between it. But keep in mind, your server's just sitting there doing nothing. It's still consuming instance hours. So you're paying for what you use in terms of how much server capacity you're allocated, but it does not mean that an idle cluster is not going to cost you anything. So if you're not going to be using your OpenSearch cluster, make sure you shut it down. It also offers a high level of network isolation that you can achieve with Amazon VPC. And in addition to that, you can ensure data security by encrypting your data at rest and in transit using keys, and you can manage authentication and access control using Amazon Cognito and IAM policies as well. It also integrates with IoT. Well, one good use case is sending data into OpenSearch from your devices from your Internet of Things, which can then be analyzed and visualized. It also offers zone awareness, so you can actually allocate nodes in your OpenSearch service cluster across to different availability zones in the same region. By doing that, you can increase your high availability of these services, but it can cause increased latency. Of course, other integration points of OpenSearch service include S3 buckets via Lambda to Kinesis. You can use sort of a Lambda function as an intermediary between Kinesis and OpenSearch to pipe data in from S3. It does integrate with Kinesis data streams as well in the same manner. And you can also integrate OpenSearch with DynamoDB streams to receive data from that, and it also integrates with CloudWatch and CloudTrail for auditing purposes and operational monitoring when you spin up an Amazon OpenSearch cluster. There are a few things you can be expected to ask that are kind of specific to Amazon's implementation here. One is, how many dedicated master nodes do you want? And you have to choose how many of them and what instance type you want to use. Now, the master nodes are only used for the management of your OpenSearch domain that you're creating, and it does not hold or process any data. So generally, you don't need too many of them unless your cluster is really massive. What's a domain? Well, again, this is sort of an Amazon-specific thing. And an Amazon OpenSearch service domain is a collection of all the resources needed to run the OpenSearch cluster. So it contains all the configuration for the cluster as a whole. So basically, a cluster in Amazon OpenSearch parlance is a domain. It also allows you to enable automatic snapshots to S3 for data backup purposes. So if you do inadvertently shut down your cluster, you won't lose that data. And like we talked about, zone awareness is also an option if you want increased availability at the price of higher latency. Security is always an important point on the exam, so let's talk about how Amazon security systems integrate with Amazon OpenSearch. We'll dive into this when we go into the exercise a little bit more. It does allow resource-based policies, so you can attach those to the service domain that determines what actions a principal can take on the OpenSearch API. You can also have identity-based policies using IAM policies or IP-based policies to tie specific actions to specific IP ranges as well. You can also sign your requests going into Amazon OpenSearch. In fact, you have to. All requests to Amazon OpenSearch must be signed, and when you send in requests from the AWS SDKs to OpenSearch, that will give you the means you need to actually digitally sign all those requests going in. Otherwise, all that traffic would just be an unencrypted JSON data, and that's obviously not a very secure approach when you're sending stuff in flight across the internet. Now, for further security, you can also put your cluster in a VPC instead of making it public, and that will give you additional security to your OpenSearch cluster instead of having it accessible from the outside world at all. Of course, that does make it harder to actually connect to your cluster and use tools like the dashboard, but we'll talk about that on the next slide. Now keep in mind, you cannot set up your cluster first in a VPC and then move it out of the VPC or vice versa. You have to decide up front if your cluster is going to live in a VPC or be publicly accessible. You can't change that later. And finally, it integrates with Cognito, and primarily that's useful for the context of talking to dashboards, formerly known as Kibana. So the thing is, if you're hosting your OpenSearch cluster within a VPC, how the heck are you going to access your dashboards on it through the internet, through a web browser? You access the dashboards through a web interface, so it needs to be able to go inside your cluster and open up an HTTP connection to actually view and interact with the dashboards. So the simplest way of dealing that is with using Cognito. AWS offers an integration with the Cognito service, which allows end users to log into the dashboard through an enterprise entity provider, such as Microsoft Active Directory, using SAML 2.0, and also through social identity providers, such as Google or Facebook or Amazon. So you could set things up so that Cognito is allowing people to log in using their Facebook account or what have you, and that will grant them access to actually get into your dashboard, even if it's hidden behind a VPC. You can also set up secure, scalable, and simplified sign-on experiences using Amazon Cognito user pools. That makes it a little bit easier to manage these things, but getting into a VPC from the outside is still hard. Now, there are ways around it. One of them is to use a reverse proxy server, and that's what we're showing here in this diagram to the right here. So Nginx is an example of a reverse proxy server that you could run on some EC2 host somewhere, and that would then turn around and forward your request to your OpenSearch domain within the VPC. You could also open up an SSH tunnel on port 5601, which is what the dashboard listens on. And other options for getting inside your dashboard from your VPC would include VPC Direct Connect, or just using a VPN to get in there. There are some anti-patterns and ways you should not be using Amazon's OpenSearch service. These come straight out of the AWS Big Data White Paper, which again I strongly encourage you to read. One is OLTP. Although it is really fast, it's not really intended to be hit like a web service, so it doesn't have any transactional support like a real database would. If you're going to be doing stuff like that, RDS or DynamoDB might be a better choice. Ad hoc data querying. Well, I'm not really sure that's why that's an anti-pattern, because you definitely can do that using dashboards, but AWS would rather you use Athena for that sort of a thing because, well, that's what that service is really made for. But remember, Amazon OpenSearch is primarily for search and analytics. That is primarily the bucket that Amazon OpenSearch fits into. So if you're looking for a search or an analytics solution for a problem, Amazon OpenSearch might be a potential solution for that. One way Amazon has extended Elasticsearch is by adding different storage types for cold, warm, and hot storage. Let's talk about that a little bit because you might be asked about it. So your standard data nodes use what's called hot storage by default, and this is storage on your data nodes that's right there in the node, either through an instance store or through an EBS, Elastic Block Store volume. This will give you the fastest performance. It's just like, normal storage on an EC2 instance, so it's the default what you'd expect to get, but it's also the most expensive. So as an alternative, they've offered something new called ultra-warm storage. And ultra-warm storage, which they also call warm in the documentation pretty much interchangeably, this uses S3 to actually back the data, plus a caching layer to make it, well, warmer than warm, and, well, maybe ultra-warm, I guess is what they're calling it there. Ultra-warm storage is best for indices that have not a lot of writes going to them. So for things that are immutable, like log data, ultra-warm storage might be a good choice for that. It is slower performance, but it's much lower cost because you're using S3 instead of local storage. Now, in order to use ultra-warm storage, you need to have a dedicated master node. And in practice, you usually have 3 of them, but we'll talk about that more in a bit. You can't just have a standalone cluster without a master node if you want to use different storage types. And if you want to save even more money, there's cold storage available now as well. That also uses S3 to back it up, and it's even cheaper. This is intended for uses like periodic research or forensic analysis on older data. For example, if you have really old log data that you just don't care about that much anymore, cold storage might be a good place for it. Again, you must have a dedicated master, and you also have to have ultra-warm enabled as well in order to use cold storage. One gotcha with cold storage is that it is currently not compatible with T2 or T3 instance types on the data nodes. And if you are using fine-grained access control, you need to map users to the cold manager role in OpenSearch dashboards to use it properly. So a couple of implementation details there. And you can also migrate your data between different storage types as you want. And as we'll see, there's ways to actually automate migrating data from hot to warm to cold storage over time if you want to. So you don't have to decide up front what kind of storage you want for your data. You can actually move data in your indices back and forth between them as needed. And that leads us to index state management. Really more of an Elasticsearch feature in general. And, we could talk for hours and hours and hours about the details and depths of Elasticsearch itself. There's a whole course I have on that lasts forever, but we're just going to talk about enough to get you through the exam here. So the idea of index state management, or ISM, is to automate index management policies, and what are some examples of that? So for example, if you have old indices that you want to delete after a period of time, maybe you have indices that are broken up by month or something, and you only care about data within the past 3 years, you might have an index state management policy that automatically deletes those old indices after a certain amount of period of time has elapsed. You might also use it to move indices into a read-only state after some period of time. You might need to do that for compliance reasons, to make sure you're not messing with data after the fact. And like we talked about in the previous slide, you can also use this to automatically move indices from hot to ultra warm to cold storage over time as well. So if you know that you're going to be accessing your data less frequently, the older it becomes, it might make sense to automatically move that into cooler and cooler storage as time goes on in order to save some money. You can also use index state management to reduce your replica count over time as well. So if you have an index that's if you care less about it as time goes on, you could reduce its replica count over time too, if you don't care as much about losing that data over time. And you can also use it for automating index snapshots, for just backing up your index and putting it somewhere. ISM policies are run every 30 to 48 minutes. That's a weird number, isn't it? The reason that it has that range is because there's a random jitter introduced to it to make sure that you're not running index data on all of your indices at the same time. That might end up impacting the performance of your cluster. Also, you can set index state management up to send notifications once they're done. And one thing that's kind of specific to Amazon is you can even send a notification through Amazon Chime to a room to let it know that a policy has been enacted. More index management stuff. Index rollups. So you can also periodically roll up your old data into summarized indices. So this can save you a ton of money on storage costs. If after a certain period of time you don't need detailed information but just the summary information, this is a great idea for saving money. So that new rolled up index might have fewer fields. Maybe you're throwing away some fields that you don't really care about after a certain period of time. Or coarser time buckets. That's another way you can consolidate stuff. Also, index transforms are available. Same idea as rollups, but the purpose here is not to summarize data, but just to analyze it differently, to create a different view of it. And you might do things like groupings and aggregations there. So for example, I could group all of my data by some identifier and have a separate view that's grouped by that separate field that I care about. Or I could have aggregations. Maybe I care about the sum of everything within that group, or the sum of everything within a certain period of time, or the average, whatever it might be. An index transform can automatically create those new views for you. Let's also talk about cross-cluster replication in the context of index management. So you can actually replicate your indices and mappings and metadata across different domains, and this is important for a couple of reasons. First of all, it ensures high availability in the event of an outage. So if you're replicating all of your data to some other cluster that's in another data center somewhere, or maybe even a different region, if that region goes down or that data center goes down, you'll still have that backup copy running someplace else because you were replicating it. Also, it's an idea to reduce latency if you have a global application. So you can replicate your data geographically around the world using replication for better latency from different locations around the world. So if you have someone trying to hit your OpenSearch cluster from Europe, it's better to have a replica of that cluster in Europe than making them go across the ocean to hit a cluster that's located in the United States or something. The way it works is you set up what's called a follower index that pulls data from what they call a leader index. So the leader index is basically your master copy, and the follower is going to be the replicant. Just the terminology they use there. And to use cross-cluster replication, you need to have fine-grained access control enabled on your OpenSearch cluster and node-to-node encryption to make sure that we can do that securely. There's also a feature that's similar called remote reindex that allows you to copy indices specifically from one cluster to another cluster on demand. So if you don't need to replicate the entire cluster itself along with all of its mappings and metadata, remote reindex allows you to copy just an index from one cluster to another whenever you need to. A few notes on OpenSearch stability that you might need to know about. So first of all, it's important to have at least 3 dedicated master nodes. That's the best practice. If you have one, it might go down, and then you're out of commission, right? You can't just have a single master node because that's a single point of failure. Why not just have 2? Well, the problem with 2 master nodes is that you can get into what's called a split brain condition. And there can be a failure mode where you have two master nodes at the same time, basically, and nobody knows which one is the actual authoritative master node. So by having three master nodes, that third one gets to decide who is the actual master in that case. So by having at least three master nodes, you can avoid the split brain failure mode, and you can avoid the single point of failure of just having one. So that is considered the best practice. Also, make sure you don't run out of disk space. That's actually the number one problem with OpenSearch and Elasticsearch clusters in general. So you got to do the math. Make sure you're allocating enough storage capacity for what you want to store. And I haven't heard any reports of the exam going into this level of detail, but this is the sort of thing that they like to ask about. So if you do need to estimate your storage requirements for a given set of data, one way to roughly come at what you need is to take the size of the source data itself that you're trying to store times 1 plus the number of replicas. So obviously you need to account for all that data being stored on your primary cluster plus any replicas that you might be replicating it to for backup purposes or for latency purposes like we talked about, times 1.45, and that's just an estimate of all the overhead associated with storing that data. Also, you need to choose the correct number of shards. That too is a bit of a science, and unfortunately it's something you just kind of have to experiment with to get the right balance there. But they also offer an equation here that at least gets you in the ballpark. So the idea here is to take the size of your source data plus how much room for growth you want to bake into it. You know, how much do I want to assume that I want to have excess capacity for growth of that data over time, times 1 plus indexing overhead. So what is indexing overhead? Well, it's not just storing your data, it's also storing data about what's needed to index that data, and that takes additional space. Typically, that's about another 10%. So roughly, you can use that as an estimate, although you can actually query your indices to get the exact number. There's a couple of commands that you can send to it to say, give me the exact size of this index, and you can take that data, compare it to the size of the data itself, and figure out the actual indexing overhead for your specific index if you need to. But 10% is a good guess. Then divide that by your desired shard size, how much data you're putting in each shard, and that should give you an estimate of the total number of shards that you need to hold your data. Now, in some rare cases, you may also need to limit the number of shards per node. However, in practice, this usually doesn't become a problem. You usually run out of disk space before you run out of shards per node. Also, you need to choose your instance types wisely. Again, you need at least 3 data nodes for all the same reasons. 1 is a single point of failure, and 2, you can get into weird states. At least 3 is the best practice. And mostly you just need to think about your storage requirements. So again, OpenSearch is very storage heavy. So you're going to be thinking mostly about how do I get the right nodes with enough storage. Some examples would be m6g.large.search. These are all .search instance types. Or if you need something bigger, i3.4xlarge.search. And if you're actually storing petabytes of information, you might opt to use the i3.16xlarge.search instance type. A few quick notes on optimizing performance of your Amazon OpenSearch cluster. One thing to think about is memory pressure in the JVM, and a couple of scenarios that can result in that are having unbalanced shard allocations across your nodes. So if you have a certain set of shards that are doing most of the work and a few that are just sitting there doing nothing, that can cause memory pressure on the overworked shards. And when you run out of memory, bad things happen, right? You start swapping memory to disk in your performance tanks, so often that can result in performance issues. Also, having too many shards in a cluster can also cause trouble. Sort of a fundamental truth of distributed computing is that less can be more sometimes. The act of distributing that processing often takes more work than you think, and specifically can take a lot of memory to manage it all. So the takeaway from all this is that if you're seeing JVM memory pressure errors in your logs, often you can fix that by having fewer shards to yield better performance. And the way to get fewer shards is by deleting older unused indices if you can. So if there's a way to offload data from your cluster into some archive where you don't need it as much, maybe you can unload data off to Glacier or something and delete the indices associated with that old unused data, that might be a good way to get around that JVM memory pressure error. Or maybe you have indices that just aren't used at all. Get rid of them, that'll help too. So yeah, just a quick note here on avoiding the JVM memory pressure error specifically within Amazon OpenSearch. So let's walk through the example of our near real-time log analysis exercise here. What we're going to do is something that you might see pretty often in the real world. We want to build a system to be able to analyze and visualize what's going on in our server logs in near real time. So what we'll build in this activity is we're going to start with some real HTTPD logs that are sitting on our little EC2 host, and we will use the Kinesis Data Firehose agent to transport those logs in near real time through Firehose into Amazon OpenSearch service. So again, this is near real time because we're using Firehose. So, at best we're looking at a minute delay, but for operational purposes, that's probably okay. But what we'll have here when we put these things all together is a system that can allow us to interactively analyze and visualize what's going on in our log data. So for example, if we have a flurry of 500 errors indicating that there's some crash happening on our server, maybe I can use Amazon's OpenSearch service and the dashboards in it to quickly narrow down when that happened and maybe get some insight into why it happened and how to fix it. So we're going to build this thing, a real HTTP log analyzer and visualization tool using Kinesis Firehose and Amazon OpenSearch service. So let's dive in and get this thing built. So let's start by connecting to our EC2 host that we're using for this course. We should have set this up earlier, and I'm just going to use EC2 Instance Connect to make life easy. And we're in. All right. So first thing we're going to do is download our sample HTTPD log data. So just type in the following command to get that from my server, wget http://media.sundog-soft.com/aws-big-data, pay attention to capitalization, /httpd.zip. And this will give you some real web server logs from one of my own personal websites here. Let's unzip it. And now we're going to move that into a directory where the Kinesis agent can find it after it's done inflating. All right, there we go. Let's go ahead and move that. So sudo mv, we're going to move the entire HTTPD folder into /var/log/HTTPD. All right, so let's make sure it's there. Yep, cool. All right, so the next step is to create an Amazon OpenSearch cluster to receive this data. So let's go to the AWS console, and under services, I'm going to go to, well, I guess we'll have to search for it, OpenSearch. There it is. Amazon OpenSearch service, successor to Amazon Elasticsearch service. Again, you might see those names used interchangeably for a while still. Let's go ahead and create a new domain. Again, these are not cheap, so let's make sure we don't have this running any longer than we need to. Be sure to complete this exercise once you start it within a reasonable amount of time. Okay, we need a name for our domain here. And again, the domain is what our cluster is called. We'll call it Cadabra, because we're going to pretend this is coming from our fictitious Cadabra web server fleet. We do not need a custom endpoint. We are just going to be doing development and testing. We want to keep this cheap. So let's go ahead and select that option. OpenSearch just came out, so version 1.0 is all that's available right now. They still have the old Elasticsearch versions here available too. So let's see how long that sticks around for, huh? Don't need compatibility load necessarily, but this is worth talking about. So if you were using the old Elastic stack prior to Amazon branching it off, and you wanted to use things like Logstash or Beats, there is a compatibility mode available here, so you can actually use Elastic technologies with Amazon OpenSearch. But we're not going to need this for this situation. We're not using Logstash. We're using Kinesis to actually shuttle these logs in. Autotune is a neat feature that automatically optimizes your cluster performance over time. There's no real reason not to have that on, so let's go ahead and leave that enabled. I'm going to stick with the default instance type because that's usually a safe bet. But I only want one node because, again, I'm cheap and I'm only using this as a little test case here. I'm not in production. I have a small amount of data. All I need is one node, so I don't want to pay for 3 of them. Storage type of EBS is fine. We're going to leave those defaults as is. I do not need a dedicated master node because, again, I'm just trying to save money here. But if you did have a real production domain, you would definitely want one. And in general, when you have a single point of failure like a master node, you want to have at least 3 of them. That way, if one fails, you'll have 2 more that can elect a new primary between the 2 of them somehow. But again, for just test purposes to save money, I'm going to keep this off. But for a real production system, you would definitely want 3 or more dedicated master nodes in place for best performance and best reliability. I don't need to mess with the warm and cold data storage stuff here. We would need dedicated master nodes to do that anyway, so since I don't have any, I can't set that even if I want to, but interesting option here that I can actually specify what kind of underlying data storage I want and what I want to pay for that, basically. Right now, only hourly snapshots are available, so okay, we'll stick with that. And I'm going to actually open this up to the public internet to make life easy. Again, in a real world deployment, you'd want to think about that. We talked about in the slides some ways of actually accessing your VPC such that you can access the dashboards we're going to create from your web browser at home. But just to make this exercise a manageable length, we're going to keep it simple for now and make that public access. Now, I'm not going to go crazy and open this up to the entire world. I am going to tie this down at least to my IP address, so nobody outside of my house can get into this. So sort of a compromise there for security, but remember, security is a big deal. You want to think about that in more depth in the real world. So to that end, I do not need fine-grained access control. I'm just going to tie this to my IP address to keep it simple. Note that they do have an option for SAML authentication if you want to use a single sign-on system for OpenSearch dashboards, formerly known as Kibana. That's another way of actually managing that access. But again, we're just going to cheat by making it publicly accessible but open to my IP address. Also, you could use Cognito as a choice for logging into dashboards of Kibana as well. Like we talked about, there's a lot of ways of managing that secure access to your dashboards inside of a VPC if you need to go there. But what I'm going to do is just configure a domain level access policy, and I'm going to set that to my IP address. So I'm going to say configure domain level access policy, set the type to IPv4 address, and I just need to find out what my IP address is. So there's websites out there like whatismyip.com that will tell you. So at the moment, my ISP has assigned me this IP address. We'll probably change tomorrow. And we'll go ahead and paste that into Principal here. And we'll say we'll allow traffic from that IP address. All right. So the rest of the options we can probably leave to their default. We absolutely want encryption. So we want to keep everything secure, of course. There's no reason not to. We'll allow the AWS owned key to use. If you wanted to choose your own key, you could do that instead. I don't need any tags, and I do not need any advanced settings here as well. So let's double check everything here, review what we set up. This is all on one page now. This used to be broken out into several steps, so a little bit of a UI change there recently. Our domain is called Cadabra. It's a development and testing, version 1.0 of the new OpenSearch system. We are leaving AutoTune on. We only have a single r6g.large.search instance type. We do not have dedicated master nodes because we're cheap. That limits our choices for the data storage, and we only have the choice of hourly backups, so that's fine. We are opening this up to the public without fine-grained access control, without SAML, without Cognito, but we are locking this down to our own IP using a domain-level access policy. All right, looks right to me, so let's go ahead and hit Create. And we have to give that some time to spin up. It says it takes 10 minutes, but in my experience, it's closer to a half an hour. But let's use some of that time to create our Firehose delivery stream that we're going to use to actually transport data from our server hosts into OpenSearch. So let's go back to Services and go to Kinesis Firehose. Kinesis Data Firehose. All right, let's create a delivery stream. And the source in this case will be a direct put, because that's going to be coming directly from the Kinesis client running on EC2. The destination, of course, will be OpenSearch. We need to give our stream a name. That's not a very catchy one. Let's just call it Weblogs, capital W, capital L. Be careful, getting that name right is important because we'll need to transcribe that into our Kinesis agent on EC2. Now we do want to transform source records. So coming out of the Apache log data, we need to transform that into a JSON format that Amazon OpenSearch service can understand. So we do need this step. Now it would be possible to set this up on the client side, but it turns out that handling the timestamps properly for OpenSearch is a little bit tricky. So it's actually advantageous to use Lambda for this. It's also more scalable this way, right? So this way we're putting the load of the transformation into Lambda and offloading that from our actual web servers. In the real world, you don't want to add any more load to your web servers than you need to, right? So it's enough that we're asking those web servers to transfer those logs to us through Firehose. Why bog them down further by making them transform those records as they're being streamed as well? The job of those servers is to serve the web pages for your website, not to transform that data. So we're going to let Lambda do the work there. So we'll say enabled, and we're going to create a new function for this. Fortunately, there's a blueprint for this, Apache log to JSON. We can just click on that. And say use blueprint. All right, so this is actually not just a function. It's actually a Lambda application that contains a function as well as an IAM role. So it's a little bit more complicated, but easy to use. All we have to do is scroll down and fill in a couple of parameters here. One is the name of the function that we want to create, the Lambda function. So let's go ahead and call that log transform. Again, we'll have to remember that later on. And the table name, where it's going to put all the stuff, we can call that anything we want, really. How about web logs? That'll be the name of the table we're storing the stuff in. So let's go ahead and hit deploy and wait for that to get created. All right. We have our Lambda function for transforming the log data into JSON. If we go back to Firehose now, we should be able to choose that. So let's go ahead and hit browse. Let's go ahead and select that. One thing I'm noticing though is that the timeout is only 3 seconds, so we're going to want to increase that. It's giving me a warning about that right now, actually. So let's go ahead and fix that while we're at it. Click on that. Go to configuration, and we'll edit that and change the timeout to 1 minute. That's better. All right, back to Firehose. We'll go ahead and choose that function now. And let's keep on scrolling here. Buffer interval of 60 seconds is good. It's the minimum, so we want to make sure that our data is getting pushed across as frequently as possible. Since this is going to be used for operational troubleshooting, faster is better. 3 megabytes should be more than enough. We're not pushing that much data across in our case, but again, that is something you can increase if you need to. All right, we need to select the domain of our OpenSearch service. Let's see if that's actually available yet. It is. No, it's still processing. So we're going to have to wait for that to actually finish spinning up. So go ahead and hit pause, and we'll come back when our OpenSearch domain is ready to go. Let me open that up in another window so I can keep an eye on it. According to that, it's up and running. Might have just finished. Yeah, it says active, says green. All right, let's try it again. Back to Firehose, browse. Still says processing. Oh, there we are. Just had to refresh it. All right, let's go ahead and select Cadabra then. Very cool. All right, index. We need an index name. We called it web logs in the Lambda function, so we need to match that index name there. Let's rotate the indices every day. That way we'll have things partitioned automatically on a daily basis. We don't want to keep all of our logs forever into one big index. Let's see. As I mentioned before in the slides, type is deprecated, so we can't even enter a type name if we want to. We just have one type per index, and it is what it is. Types as a concept are just going away. We'll keep the retry duration at 300 seconds. That's fine. Let's give it a backup bucket. So go ahead and click on Browse, or create a new bucket if you need to. I'll just use one that I have sitting around. Let's throw it in here. Actually, let's throw it in there. And you can give it a prefix. So let's give it a prefix of ES/ so that everything will be in a ES directory within that bucket, so it's all neat and tidy. And we're pretty much done here, I think. Any advanced settings I care about? Here's where we can set things about CloudWatch error logging if you want to have that enabled by default, sure. Permissions are automatically creating an IAM role for me. That's fine, that should work out well. Don't need server-side encryption, but you could if you needed to, if it was sensitive data. Let's just review everything. Again, direct put to OpenSearch service. We're calling this delivery stream web logs. We are transforming using our Lambda function to go from logs, Apache logs to JSON, sending that into our Cadabra OpenSearch domain into an index called web logs, rotated every day. And any errors are going into the backup S3 bucket I selected under the ES directory. All right, let's create that delivery stream. All right, our stream has been created. We'll take up to 5 minutes for that to actually be up and running, but we'll use that time to set up our Kinesis agent on EC2. So let's go back to our EC2 instance. Is that still running? Yeah, it timed out on me, so we'll have to close out that window. And go back to EC2 and select the host that I'm using for this course. And connect to that with the Instance Connect. All right, so let's configure our Kinesis agent to actually talk to that Kinesis delivery stream that we just set up. So we'll say sudo nano /etc/aws/kinesis/agent.json. And you should still have a Kinesis endpoint set to nothing and a Firehose endpoint set to firehose.whatever region your account is based in .amazonaws.com. That should be set up from an earlier exercise, but if not, you might need to go look that up. You can just head on over to your dashboard here, and if you look under the region here, you should be able to see that in my case, I'm in US East North Virginia, which is US East 1. You might be somewhere else, so if so, substitute your region into that endpoint. We're going to add a new flow. I've already deleted the one that was there before, so go ahead and do that if you need to. Control K, by the way, is a quick way to delete a whole line in Nano. And we're going to add the new flow like this. So quote file pattern, quote colon, quote /var /log /httpd /ssl_access star, quote comma. Be very careful typing this in, because one little typo will cause it to not work and you'll have a very hard time figuring out why it's not working. Basically, if you have any typos in this file, you'll see that nothing's actually getting pushed into your Firehose delivery stream, and it's not going to tell you why. You have to kind of like guess. Moving on. Delivery stream. That will be web logs, the name of the stream that we just created. And just to be safe, let's double check, make sure that's the name of it. Yep, web logs. And as you may recall, varlog httpd is where we unzipped those sample logs that we downloaded earlier. And finally, initial position. We're going to set that to start_of_file. That way it will start at the beginning of those logs, even if I run it again. So that will save you some pain if you try to run this multiple times. So by explicitly saying I want to begin at the start of the file every time, that's just for debugging purposes, so I can actually replicate processing the entire log every time while I'm testing things out. All right, double check things here, make sure there's no typos. Very easy to do, very easy to miss a comma, very easy to miss a star, very easy to just type something wrong. So take a moment here and double check. Looks right to me though, so I'm going to go ahead and save that. Control O. Enter, Control X. All right, so now we can kick this whole system off. We've got everything put together. We have our Kinesis agent configured on EC2. We have a Firehose delivery stream configured to receive that data. And we have an Amazon OpenSearch cluster ready to receive that data from Firehose. So let's kick it all off and say sudo service aws/kinesis-agent restart. And that should cause it to pick up our new configuration file here that will tell it to pick up the SSL access logs within varlog HTTPD and begin at the start of the file. So let's go ahead and tail the log and see what's going on. tail-f/var/log/aws/kinesis-agent/aws kinesis agent log. Okay, we can see that it's already started up, and hopefully it will start to send some data. All right, and we can see that it's successfully parsing records here, 364,500 at a time right now, it seems. So it looks like things are processing successfully. Now, if you do see 0 records parsed, a few things to check. One possibility is that you actually had the Kinesis agent running while you were putting those new log files into place. So one thing you can try is actually stopping the Kinesis agent, moving those files back in, and then starting it again. But odds are this is what you're seeing if you don't have any typos in that configuration file. So now we can go and play with this new data that we've been importing here. So let's go ahead and confirm that the data is flowing. Let's go back to our console and go to OpenSearch. And let's select our domain, Cadabra. And let's see, if we go to indices, sure enough, there's our weblogs index, which is rotated by day, so we automatically have the day there that I'm running this on. And you can see that I do have a bunch of documents in there, so that's a good sign. All right, let's try to visualize it. So to do that, we're going to use dashboards. Pretty easy to do now, a lot easier under OpenSearch actually than it used to be. Let's go ahead and just click on this link up here to OpenSearch dashboards URL. And again, since we did make this cluster publicly accessible but limited to my IP, there are no security issues I need to get around here. All right, and you can see that you can actually add data explicitly from other sources here, but we're already piping this into our OpenSearch cluster here already. So our data is sitting there, we just need to tell it about it. So let's go ahead and explore on my own. So let's click on this manage link here. And we want to set up an index pattern. So let's create an index pattern. And we know our index starts with weblog. So we're just going to say weblogs star and see what comes up. There it is. Awesome. All right, so let's go ahead and hit next step. Our time field will be at timestamp. We want local time, make life a little bit easier, and create an index pattern. So now we can actually work with this data in this index interactively. And it's going to tell me what sort of schema it extracted from that. Looks like we successfully converted things into JSON using our Lambda function, so that's cool. Cool. All right, so let's do something with this. Let's open up our little menu here and go to Discover. And we've already tied things to our index here. Now it's saying there's no results, and that's because it's only looking by default in the last 15 minutes. However, these are weblogs that go back to the year 2019. So to view that data, I'm going to have to change the time range up here. Let's go ahead and change that. Click on Show Dates. And we're going to change from 15 minutes ago to an absolute date from 2019. And this data actually starts on January 27th, it turns out. And instead of going to now, we'll again use an absolute time, again in 2019. And this data ends on February 2nd. And update. And now we have some data. Cool. So we're actually seeing the contents of our OpenSearch database here. And we can see each individual log line that's been transformed into JSON. So it's all nice and structured here into different fields that we can search. And not only can we search it, we can visualize it and make graphs out of it, kind of like this. So let's imagine that there was some sort of an operational problem during this time period, and I need to narrow down when it happened and why. Well, that's easy to do. Let's go open up the menu again and go to Visualize. And what we want to do is create a new visualization that will let us visualize 500 server errors over time. So I'm going to do that as a vertical bar chart. We'll select our index as the source of that data. So first of all, let's set up a filter to just get 500 errors. So I'm going to look for the response field and make that is 500. So that way I'll visualize only 500 server errors that are coming in from that data. Now I want to visualize that by time, let's say by the hour. So let's change our buckets here. Let's add a bucket on the x-axis and make that a date histogram. And the interval will be hourly. Update. And there you have it. So we can see that there was indeed a spike of 500 errors right at 8 p.m. Is that? Yeah, 8 p.m., 2000 hours. Cool. So there were 500 errors that came in during that time. Depending on how many times you actually ran that log activity, it might be less than that. So don't get too hung up on the actual number there. But you can see that I can drill into that and say, hey, 500 errors during that hour. Cool. So that gives me something to look at. What happened at 8 o'clock on January 29th of 2019? It's kind of the first step into troubleshooting this. So cool, there you have it. We've actually gone through the entire pipeline of setting up some fake server log data on an EC2 host, using the Kinesis agent to put that into a Kinesis Firehose delivery stream. That delivery stream is using a Lambda application to transform the data using Lambda from Apache log format to JSON format, and then finally feeding that JSON data into OpenSearch. And from OpenSearch, you can see that we can interactively query and visualize that data as need be. So we've really built a little operational system here pretty quickly without a whole lot of work using AWS. Cool stuff. Let's clean up our mess here, right? Because this stuff is not free, remember, OpenSearch in particular. So first thing I want to do is shut down my EC2 host. Let's go ahead and Control-C out of that log that I'm tailing. And I'll exit out of this console. And let's go back to EC2. And I'm going to go ahead and stop that instance. Next, I'm going to kill my delivery stream because that actually costs money too, even if it's just sitting there. So let's go ahead and delete that delivery stream. To do so, I need to confirm. And even more importantly, we need to delete that OpenSearch cluster because that's going to be super expensive if I don't. So we'll go back to OpenSearch service, select the Cadabra domain, and hit delete. Yes, I'm sure. We need to confirm the name of the domain and hit delete. So that's being deleted. And finally, we had that Lambda function that we might want to clean up. So let's go back to Lambda. Getting rid of a Lambda application is a little bit complicated, so we can see what happens when I try to delete that. Let's select that and say delete. It'll say, no, this is actually an application stack. There's more than just a function here, so I need to delete it from AWS CloudFormation. Fortunately, though, it gives me a handy link to it. And from here, I can delete it. And we can see that delete has been initiated for that as well. All right, we cleaned up our mess, and that was a good exercise. So I hope you guys found that interesting and a good hands-on practical experience in tying together Kinesis Firehose, Lambda, and Amazon OpenSearch service. Next, let's dive into Amazon Athena. It's a really cool query engine for doing interactive queries on your data in an S3 data lake, and it's completely serverless, which is really super interesting. So what is Athena? Its official definition is an interactive query service for S3, so basically it's a SQL interface to your data being stored in some S3 data lake. There's no need for you to load your data from S3 into Athena. The data actually stays in S3, and Athena just knows how to interpret that data and query it interactively. Under the hood, it's using Presto. You might remember Presto from our Elastic MapReduce lectures, and it's just a very highly customized and pre-configured Presto instance for you with a nice little user interface on top of it. But the great thing about Athena is that it's completely serverless. So you do not need to manage any servers. You don't need to provision servers. You don't have to even think about how it works. You just think about using it, really. Athena supports a wide variety of data formats that might reside in your S3 buckets. Those include, and these might be important to remember, CSV, JSON, ORC, Parquet, and Avro. And this is as good of a time as any to get into how these different formats differ from each other, because depending on your application, a different format might make sense, right? So the good thing about CSV, which is comma separated value, and its cousin TSV, tab separated value lists, is that they're human readable. You can look at them in a text editor and make sense out of the data that's in there very easily. It's just one line per row of data. Every line contains a bunch of fields separated by commas. Easy peasy, right? Same thing with JSON. JSON has a bit more structure to it in that you can have more hierarchical data inside of it, but it's still human readable. So it's still one row per document, and each document is something you can look at and understand. But then if you want to really do things at scale and do things more efficiently, you should be looking at maybe non-human readable formats, such as ORC and Parquet. ORC and Parquet are both examples of columnar formats that are also splittable. So instead of organizing data by rows, it's organizing it by each column. So if you have an application that's doing queries on your data based on specific columns, like let's say you have a use case where you're always looking up records by their, user ID or something, that columnar storage makes it very efficient to go and retrieve data for a specific column's value. The other advantage to ORC and Parquet is that they are splittable. So even though they're organized and compressible in very cool ways, they're still splittable. So in a big data setting, those files can still be split into chunks that can be distributed across an entire cluster. So you can still have a massive ORC or a massive Parquet file and still have the ability for your cluster to split that data and view it across different instances. Avro is also an example of a splittable file format, but it is not columnar, so it is not human readable. However, it is for more row-based storage where you might be looking at an entire row's worth of data at a time, generally speaking. But it is still splittable. So it's important to remember that these are all splittable formats because that can be important on the exam. All right, let's put that little diversion aside and get back to Athena. So another important point is that Athena doesn't really care if your data in S3 is structured or semi-structured or structured. It can work with Glue and the Glue data catalog to impart structure on that data and make it something that you can query from a SQL command. Some examples of usage here given by Amazon include the ad hoc querying of web logs. So Athena is given as a better example of how to deal with querying web log data in S3, and they would rather have you use this than Elasticsearch, for example. You can also use it for querying staging data before loading it into Redshift. So maybe you have a bunch of data being dumped into S3 and you want to transform it and load it into a big Redshift data warehouse, but maybe you want to be able to play around with that data and investigate it and see what it looks like beforehand. Athena might be a good way of sort of getting a bigger picture of what that data looks like before you actually commit it into a data warehouse. It's also useful for looking at other logs besides web logs in S3, including Cloud Trail logs, Cloud Front logs, VPC logs, Elastic Load Balancer logs, whatever you have. If it's in S3, Athena can query it. It also offers integration with tools like Jupyter and Zeppelin and RStudio notebooks because you can just treat it like a database. It has ODBC and JDBC interfaces, so you can treat Athena like any other relational database that you might interact with or integrate with. That also includes QuickSight. You can also integrate Amazon's QuickSight visualization tool into Athena to actually use that as sort of the glue. Well, glue's a poor choice of word because we are actually using the Glue service for this, but the thing that connects your unstructured data in S3 to a more structured visualization or analysis tool, such as QuickSight. So speaking of Glue, let's talk about how Athena integrates with AWS Glue to actually impart structure on your unstructured data in S3 so that it can actually query it like a database. So again, let's do a little brief recap on how Glue works. You might have a Glue crawler populating the Glue data catalog for your S3 data. That's looking at what's stored in S3 and trying to extract columns and table definitions out of it for you. And you can use the Glue console to refine that definition as needed. So once you have a Glue data catalog published for your S3 data, Athena will see it automatically, and it can build a table from it automatically as well. So anytime Athena sees something in your Glue data catalog in your account, it's going to make a table for that for you so you can query it just like you would any other SQL database. And it's not just Athena that can use that Glue data catalog either. It will allow any other analytics tool to visualize or analyze that data as well. For example, RDS, Redshift, Redshift Spectrum, EMR, any application that's compatible with an Apache Hive metastore as well, because remember, the Glue data catalog can be used as a Hive metastore too. But in this example, we're using it to expose that table definition to Amazon Athena. And with Athena integrated with AWS's Glue data catalog, that allows you to create a unified metadata repository across various services, crawl data to discover schemas, populate your catalog with new and modified table and partition definitions, and maintain schema versioning, all under the hood, and Athena just sits on top of that and provides a SQL interface to that underlying glue structure. So I do want to bring up a specific issue that you can run into when using Athena and Glue together like this, and that's when you're running across different regions. So the thing is, Athena cannot query across different regions on its own, but a Glue crawler can. So let's say you have some data sitting in S3 that's in a different region than where you're running Athena from. You can still get at that data if you query a Glue data catalog that's in the same region as Athena. So what you would do in this situation is set up a Glue crawler that has access to your data in the different region, but as long as that Glue crawler is populating a Glue data catalog in the same region as Athena, Athena can still access that data. Got it? So, the Glue crawler that created the data catalog may have spanned multiple regions. It can do that, but as long as the data catalog itself is in the same region as Athena, then you're good. So that's how you handle these cross-region concerns when you use Athena and Glue with S3 data that might be stored in some other geographical location. Another feature of Athena is work groups, and you definitely need to know what these are all about. Basically, it's what it sounds like. You can organize users and teams or even applications and workloads into different work groups and group them together. And you can use this to control the query access of a given work group or to track costs by a given work group. So maybe you have a specific team of people that should only have access to specific types of queries or limits on the queries that they can run, right? And you want to track their costs individually to figure out, what kind of bill they're running up for the organization. Work groups are integrated with IAM, CloudWatch, and SNS, so you can do things like have it notify you when limits are hit. And the way you use this is you can have your own data limits on each work group. So you can limit how much data queries can scan by work group. So if you want to make sure that somebody in a given team isn't going to construct some wildly inefficient query that has this huge bill that results, you can limit that at the work group level. Each work group also has its own individual query history. So, if you want to make sure that a specific team of people isn't seeing the queries that another team makes, you can break them up into work groups to make sure that each work group only sees its own query history. Work groups, of course, can also have their own IAM policies because that's how you're going to manage their permissions and what they can see. And you can also have your own encryption settings on each work group as well. So it's a good way of organizing many people in an organization and limiting what they can do and giving them specific access permissions by using work groups in Athena. So just remember, Athena work groups are a thing. You can use them to limit the access of a given group of people or to measure the cost that they're doing and to have limits on the amount of data that their queries can actually scan. The cost model is very simple because it is a serverless application. You just pay as you go for the activity that you actually consume. It charges you $5 currently per terabyte scanned, which is pretty generous. Important to remember that successful or canceled queries do count toward that scanned number there. You do get charged for those, but any failed queries are not charged. So any successful or canceled queries you will be billed for. Failed queries, however, are free. There's also no charge for any DDL operations, such as create, alter, or drop. Those are free as well. Now, a very important point is that if you want to save money using Athena, it can save you a lot of money by converting your data to a columnar format like we talked about with Orc and Parquet. So not only does that give you better performance for applications that are typically querying on a small number of columns, it can also save you 30 to 90% in terms of money as well. That's because it allows Athena to selectively read only the required columns when doing a query and processing your data. So if you're only accessing certain columns from your queries, by having a columnar format, you're reducing the amount of data that you actually have to scan with Athena. And remember, you are charged by terabyte scanned. So by reducing that scanning, you win. So remember, Athena works best with columnar formats. It can save you a lot of money and give you better performance as well. Examples of columnar formats include Orc and Parquet. All right, and in addition to Athena, of course, Glue and S3 have their own charges as well. Athena just sits on top of Glue to get the table definition for your S3 data, and your data is still being stored in S3. So there are separate charges for Glue and S3 in addition to using Athena as well. Also, I should point out that partitioning your data can also help Athena to reduce costs as well. So if you do have your data structured in S3 in different partitions, such as by date or hour or something, queries that are restricted to that given partition will also scan less data as well. So in addition to using a columnar format, partitioning your data within S3 can also save you money with Athena as well. Let's talk about security too. That's always important with Athena. It offers many different ways of securing your Athena traffic. One is through access control, who can actually get to Athena and query your information in the first place. And you can use IAM, access control lists, and S3 bucket policies to restrict access to that information. The IAM policies that are relevant here are the Amazon Athena Full Access and AWS QuickSight Athena Access policies. You can also encrypt your results if you are sensitive about the results of your queries, and you can encrypt them at rest in a staging directory in S3, and that can be encrypted in several different ways. You can, again, these are important to remember, guys, so you can encrypt your S3 data results in server-side encryption using an S3 managed key. That is called SSE S3. You can also do server-side encryption of your results using a KMS key. That's called SSE KMS. Or you can encrypt them on the client side with a KMS key as well. That's called CSE KMS. And depending on your security requirements, one or more of these may make sense. So think about how that data is flowing, where it's being stored, and how you want it to be secured. You can also have cross-account access defined in S3 bucket policy. So it is possible for you to access Athena to a S3 bucket that is not owned by your account. If that other S3 bucket has a policy that grants access to your account, it's possible for an Athena console in one account to access a data lake stored in another account. You can set that up. As far as in-transit security goes, you can use TLS, the transport layer security, for all the traffic going between Athena and S3 as well. That can be set up too for in-transit security with Athena. Always important to remember security aspects, guys. It's a huge part of the exam. Finally, let's talk about anti-patterns. Again, these come straight out of the AWS Big Data white paper of things they don't want you to use Athena for. One is for highly formatted reports or for visualization. At the end of the day, Athena is just a SQL query engine. If you want to do nicely formatted stuff or visualizing things with charts and graphs, well, that's what QuickSight is for, and we'll be getting to that shortly. Also, if you want to be doing ETL, extract, transform, and load operations using Athena, that's generally not the best tool to use. Glue is an alternative there, and using Glue ETL instead. You can also do that with Apache Spark or what have you for larger scale tasks. So that's Athena in a nutshell. Let's go and play with it, shall we? A few quick notes on optimizing Athena's performance. The exam loves to focus on topics like this. Basically, it comes down to three things that we want to talk about here. One is you're usually going to get better performance by using columnar data formats like ORC or Parquet. Athena will just work better if you can pre-process your data somehow to be in a columnar format. And you can do that with things like Glue or through an ETL transform. There's a lot of tools you can use to transform your data into a format that's more optimized for Athena's use. So if you are concerned about performance, make sure that you're using a columnar data format under the hood with Athena in ORC or Parquet. So if it's hitting S3 data, if it's in that format already, it will save you quite a bit of work. Also, remember, a small number of large files will generally perform better than a large number of small files with Athena. So if you can have a small number of largish columnar data files, that's probably going to be your optimal performance case right there. Also, take advantage of partitions. So if you're able to organize your data in S3 in a partition format that lines up with how you're going to be querying that data. So for example, if you're hitting up your data most commonly by a specific date range or something like that, then partitioning your data by date would make a lot of sense, right? Now, if you do need to add partitions after the fact, let's say that you have an existing data set in S3 that is not partitioned and you want to improve its performance by adding partitions, you don't have to totally start from scratch. What you can do in Athena is use a command called msck repair table to go back and add that metadata for the partitions into Athena. So if you do need to add partitions later on to an existing Athena database, you can use msck repair table to accomplish that. So those are the main points about Athena performance. Just remember those three things and you should be in good shape. A new feature in Athena is ACID transaction support. That means that we have strict guarantees about transactions. So you can actually have concurrent users hitting the same row at the same time and have it all work consistently. Under the hood is powered by Apache Iceberg. And to use it, all you need to do is add table type equals iceberg when you're creating a new table in Athena using the create table command. And this allows you, like I said, to have concurrent users safely making row level modifications or deletions, whatever it is, without worrying about them stomping on each other. This is actually compatible with Elastic MapReduce, Apache Spark, and anything that supports the Apache Iceberg table format. The good thing is that it removes any need for custom record locking. So without ACID support, you would need to have some sort of a solution for locking a record and unlocking it surrounding any modifications to it, so that if two people were hitting the same record at the same time and trying to write to it, they wouldn't be fighting with each other. Iceberg and ACID transactions just does that for you automatically now. Also, a little side benefit is that it gives you what's called time travel operations. So you actually have the ability to recover data that was recently deleted just using a plain old select statement. So some of the historical data that's keeping around for the purpose of ACID transactions can be used for that purpose. Now remember when we talked about governed tables in lake formation? Well, this is kind of another way of doing the same thing. So governed tables gave us ACID support on S3 tables in lake formation. But this is another way of getting ACID features with Athena. So you could set up a governed table in lake formation and then hit that table with Athena and you would have ACID support. This is just another way of doing it. So you can just create a table explicitly from Athena directly with a table type of Iceberg, and you'll get ACID support on that as well. So kind of two different ways of solving the same problem there. Now you might also remember that in lake formation with governed tables, it had a feature to automatically compact those tables over time. Because over time, there's sort of this overhead that builds up, and it can actually make your performance degrade as time goes on. Now with Athena ACID, at least for now, you do need to do that yourself periodically. So if you are using ACID transactions in Athena, you'll probably want to do a command like this once in a while. Optimize table, rewrite data using bin pack, where catalog equals whatever. So a command like that will go back and compact your data that's sort of been bloated by this ACID support over time and make it performant again. So that's the kind of thing I could see showing up on the exam, that kind of trivia. What do you do if your ACID transactions are getting slower over time? Well, the answer would be to periodically compact them using the bin pack command here that you're seeing. That's Athena ACID in a nutshell, an exciting new feature in 2022 as more and more of the AWS data analytics world goes to ACID support. Let's start building out our data warehousing and visualization requirements for Cadabra using Amazon Athena at first. We're going to do this in a couple of different ways in this course, one using Redshift and one using Athena. Let's start with Athena because that one's easier. All we have to do is set up AWS Glue to actually infer a schema from our data lake in S3, which houses all of our order data. And we've already done the work of importing all that order data into S3 earlier in the course. So we did set up a data fire hose way back earlier in the course to dump all that data into S3 for us. So we have a bunch of order information just sitting in S3 as CSV files. Now we just need to tell Glue where that is, give it a few hints about how that data is actually named, and then we can just issue queries against that data from Athena as if it were a SQL database. So let's build that out and see if it works. Back to the management console, let's get started by going to AWS Glue. Go ahead and type that into Find Services if it's not here. And we'll go to crawlers and add a crawler. We'll give this crawler a name called, I don't know, order data. The defaults here are fine. For security, it's always worth talking about security. The only option here is to encrypt your logs from Glue that are going to be pushed into CloudWatch. So we're not going to worry about that. That's not really sensitive information for us right now. So we need to choose a data store that our data lives in. So we want Glue to go look at our data in S3 and make a table out of that. Other options are JDBC sources, so you could have it on top of some other database, or DynamoDB, but for us we're using S3. Let's browse to the path in S3 where our data lives. For us that's orderlogs-sundog-edu bucket. Obviously your bucket name will be slightly different. Go ahead and select that. And we do need to exclude some stuff here, so let's open that up. If you did the Amazon Elasticsearch service exercise earlier, we did configure Firehose to dump errors into an ES subdirectory in that same bucket. So we don't want to see that data as we're building up our schema here for order data. So we're just going to say ES/** to exclude everything underneath the ES directory in our bucket. Click out of that to apply it or hit return, whatever, and hit next. We're done. That's the only data store we want. We do need to create an IAM role so that Glue can talk to S3. Let's call it, I don't know, order data. And hit next. We will run this on demand because I don't anticipate our schema changing anytime soon. And we need to add a database to actually put the information into. So let's hit add database and we'll call it, I don't know, order logs. Create. We don't need a prefix, and we're all good. Hit next. We can review everything, make sure it looks correct, and finish. All right, so we created our crawler. We want to run it now. So click on Run It Now and let it go do its thing for a bit. Take a couple of minutes for this to finish, so we'll come back when that's done. All right, after a couple of minutes, my crawler is back in ready status, and you can see that it did add one table, so that seems promising. Let's go back up to the databases here and check it out. So sure enough, there's our new order logs database. Let's click on that. And if we click on tables in order logs, looks like we now have an order logs _ sundog edu table that was created. Of course, for you, that will be a different name based on the bucket name that you were inside. And let's go ahead and take a look at what's in there. Cool. And you can see it did extract a schema. Now the thing is, we don't have any header information in the CSV data in S3, so it has no idea what these columns actually mean or what they should be called. So we're going to have to tell Glue what these column names are by hand. Also, we have 4 partition fields here. And if you recall, the data in S3 for our order logs is broken up by a year directory, and then a month subdirectory, and then a day subdirectory, and then an hour subdirectory. That's what these partitions are. They're the subdirectory structure that our S3 data lives within. And we can take advantage of those partitions to speed up our queries, which is kind of nice. So let's go ahead and clean these up and give these columns and partitions some real names. Let's hit Edit Schema up here. And we can just click on each column name and tell it what it is. I happen to have a cheat sheet here that tells me that the first column is invoice number. Invoice no is what it's actually called. The next one is stock code, followed by description, followed by quantity, invoice date, unit price, customer ID, and country. And as we said, the partitions correspond to the directory structure our data is stored in, which is the year, month, day, and hour. All right. Now it did infer the data types as well, as best it could based on the data that it saw. If you're going to be using this from Hive, don't change those, okay? Because you get all sorts of weird errors about the partition keys being different from the main keys in your data here. And it's a really difficult thing to recover from. In my opinion, it's a bug in Glue. Maybe they'll fix it someday. But if you do need to transform this data into some other type, let's say that I wanted my invoice dates to actually be a date type instead of a string, the best way to do that right now would be to create an ETL job in Glue and write a script to actually do that conversion for you there. But we'll live with this for now. This is good enough for us to play with. So let's go ahead and hit Save to apply those changes to our schema. And if we scroll down, we can see that our invoice name stuck. It's SQL, so they got all lowercase-ified, but that's fine. All right, so now we have a table in AWS Glue that gives some structure to our collection of CSV files that are sitting in S3. So kind of neat. We can start treating that S3 data lake as a database. Let's head over to Athena and see if it actually works. So back to the console here. Let's go to Athena. You might have to type that in, of course. And you can see that our order logs database is already here. How cool is that? And our order logs sundog edu table within it is already here. So it just works. I didn't have to set up any servers. I didn't have to import the table or import the database. It's just there. Like it just talks to Glue automatically and knows that it's all there automatically. So extremely easy to use Athena. Love it. We can open that table up as well and see what the actual column names and partition names are, so we can refer to them in our SQL queries more easily. And let's try it out. So just as a test, let's see if we can get a count of every item ordered from France in the month of February. Okay? Why not? Now you want to substitute in your own table name, of course, because it will be different. And you will probably also have to change the month and year in this query to correspond to the month and year that you actually uploaded that data into S3. So you might want to go check your S3 data right now and make sure that you have a year and month that makes sense. It's probably the current one if you did this all in the same month in this course, but whatever. Bottom line is this specific query will not work for you. You need to adapt it to your own data and your own bucket name. But just to show you that it works, let's type in the following. Select. description, comma, count star, thusly, from, and the table name is order logs underscore sundog edu. Again, change that to your own table. Where country equals France, and year equals whatever year you imported it in, and month equals whatever month you imported the data in. Group by description. And again, what that should do is give me a count of each item bucketed by its description for orders in the month of July 2019 that were done from France. Let's see if it works. It did. Cool. Awesome. Yeah, so there we have it. Apparently there were 15 orders of the Woodland Mini Backpack, whatever that is, and 14 Charlotte Bag Suki designs. Sounds nice. But the cool thing here is that how easy that was, right? So once you have Glue set up and you impose some structure to your unstructured data in S3, you can query that like a database from Athena. And that's a very quick and easy way to sort of explore your data and extract information from it, even do ETL sort of stuff on it at the same time. So there you have it, Athena running through AWS Glue on an S3 data lake in action. Next, let's dive into Amazon Redshift. Redshift is AWS's distributed data warehouse solution. So it is a petabyte scale data warehouse that is spread across an entire cluster, but it's fully managed. So, you don't think about taking care of that cluster. They take care of all the server maintenance for you. Now, given that the world of big data often involves the world of data warehouses and dealing with massive data sets, it should be no surprise that the exam spends a lot of time talking about Amazon Redshift. So we're going to spend a lot of time on it as well. A lot of depth here needed on Redshift, so pay attention, folks. This stuff is all important. At a high level, what is Redshift? Well, it is a fast and powerful, fully managed, petabyte-scale data warehouse service. And Amazon claims that it delivers 10 times better performance compared to other data warehouses. So not only is it massively scalable, it's super fast, and it achieves that speed using machine learning, massively parallel query execution, which is called MPP, and using columnar storage, which we talked about earlier, and using high-performance disks as well. Keep in mind, Redshift is a data warehouse, so it is specifically designed for online analytic processing, OLAP. It's for querying your data and getting insights out of it on an analytical standpoint. It is not made for OLTP. For OLTP, typically you would want more row-based storage. So you're not going to be hitting your Redshift data warehouse at massive transaction rates, expecting fast responses. It's meant as an analytics tool, which is why it's in the analytics section here. They also claim that in addition to being super fast and super scalable, it's also super cheap. They claim it is the most cost-effective cloud data warehouse, and there is no upfront cost to using Redshift, and that is in stark contrast to building out a massive data warehouse on premises. I can tell you that firsthand. You just pay as you go for the resources that you're consuming. And that can end up being 1/10 of the cost or less of traditional data warehouses that are stored on premises. Also, it provides fast querying capabilities over structured data using familiar SQL-based clients and BI tools, just using standard ODBC and JDBC connections, so it just looks like another relational database to the outside world, and you can connect any analytic or visualization tool you want to Redshift on top of it. It's also easily scalable. You can easily scale up or down your cluster with just a few clicks in the AWS Management Console, or with a single API call. So if you do need to scale it up or scale it down, that's very easy to do. Won't be automatic, but at least it's easy. It also uses replication to enhance your availability and continuous backups to improve your data durability. And it can automatically recover from component and node failures. For monitoring, it integrates with CloudWatch, and for metrics for compute utilization, storage utilization, and read-write traffic to the cluster, those are all available for you free of cost within CloudWatch. And you can also add user-defined custom metrics that you can add using CloudWatch's custom metrics functionality. It also provides information on query and cluster performance using the AWS Management Console, and that helps you in diagnosing performance issues like which user or query is consuming high resources. Some use cases that are listed for Redshift are accelerating all of your analytics workloads. So if you just want your data warehouse to be faster, you might want to move to Redshift. It uses, as we said, machine learning, MPP, and columnar storage on high-performance disks and result caching to make it super fast. You might also want to use Redshift because you want to unify your data warehouse and your data lake. Something we'll talk about shortly is Redshift Spectrum, which is a way of importing your unstructured data in S3 as just another table in your data warehouse. So you could actually do joins and stuff across your structured data that's been imported into your Redshift servers themselves, together with data lake information that's actually stored in S3 somewhere. That's kind of cool. Maybe you just want to modernize your data warehouse and make it faster and more scalable and easier to manage. Redshift is a potentially easy way of doing that. And there are some more specific use cases that come out of the AWS Big Data White Paper. Those would include analyzing global sales data, storing historical stock trade data, analyzing ad impressions and clicks, aggregating gaming data, and analyzing social trends. These are all examples of stuff you can do with Redshift, or really any data warehouse for that matter. Let's start diving deep into the architecture of Redshift itself. So basically we have clusters. That's kind of the highest level here that encompasses this entire picture here. A cluster is the core infrastructure component of an Amazon Redshift data warehouse. And a cluster is composed of a leader node, which you see here, and one or more compute nodes. You can contain between 1 and 128 compute nodes depending on the node type. So it's not infinitely scalable, but 128 nodes can hold a whole lot of data. And each cluster can contain one or more databases. Now the user data is going to be stored on the compute nodes. The leader node is just managing communication with the client programs and all communication with the compute nodes. So it's sort of the interface between your external clients to Redshift and the compute nodes under the hood. It receives all the queries from client applications, parses the queries, and develops execution plans, which are an ordered set of steps to process those queries. It then coordinates the parallel execution of those plans with the compute nodes, and also aggregates the intermediate results from those nodes. Finally, the leader node will return those results back to the client applications. Let's talk about the compute nodes in more depth. So compute nodes are responsible for executing the steps specified in the execution plans that it's getting from the leader node and transmitting data among themselves to serve those queries. It then sends those intermediate results back to the leader node for aggregation before being sent back to the client applications. Now each compute node has its own dedicated CPU, memory, and attached disk storage, which are determined by the node type you choose. There are two different types of node types you can choose for a compute node in your Redshift cluster, and you choose this when you set it up. One is dense storage, that's DS node type. That allows you to create a very large data warehouse using hard disk drives, or HDDs, for a very low price point. And these are available in two different sizes, extra large and 8XL. An extra large XL has 3 HDDs with a total of 2 terabytes of magnetic storage. And an 8XL has 24 hard drives with a total of 16 terabytes of magnetic storage on that node. Now a DS2.8XL large has 36 Intel Xeon E5 2676 Haswell virtual cores and 244 gigabytes of RAM, whereas an extra large has 4 Intel Xeon E5 2676 Haswell virtual cores and 31 gigabytes of RAM. So depending on the scale of your data, you have the choice there of extra large or 8x large dense storage if you want to optimize for storage capacity. The other option for dense storage node types is the dense compute node types. So instead of DS, we have DC node types now for dense compute. And dense compute node types allow you to create very high performance data warehouses using fast CPUs, large amounts of RAM, and SSDs, solid state disks. They're also available in two sizes, the large and the 8XL. The large has 160 gigabytes of SSD storage, 2 virtual cores, and 15 gigabytes of RAM. The 8XL is 16 times bigger, with 2.56 terabytes of SSD storage, 32 virtual cores, and 244 gigabytes of RAM. So it allows you to get started with a single DC2 large node for 25 cents per hour and scale all the way up to 128 8XL nodes with 326 terabytes of SSD storage, 3,200 virtual cores, and 24 terabytes of RAM. That's a lot. That's really big. But at the end of the day, remember that compute nodes can be either dense compute or dense storage if you want to optimize for computing capacity or storage capacity. One has SSDs, one has HDs, and within those you also have large and extra large options available to you as well. All right, so within the compute node, we have node slices. So every compute node is divided into slices, and a portion of the node's memory and disk space is going to be allocated to each slice, where it processes a portion of the workload assigned to that node. The number of slices per node is determined by the node size of the cluster. All right, that's a lot of depth there, but really you need to know it. So a cluster consists of a leader node and many compute nodes, one or many compute nodes. A compute node can be dense storage or dense compute, and that compute node in turn consists of node slices that process chunks of the data being given to it. Next, let's dive into Redshift Spectrum. Spectrum allows you to query exabytes. Exabytes, mind you, we're past terabytes here, or petabytes. We're in big data land here for sure. Exabytes of unstructured data in S3 without loading it into your cluster. So in very much the same way that Athena could use the AWS Glue catalog to make tables on top of your S3 data, Redshift Spectrum can do the same thing. It's very much the same idea. It's just that instead of having this console-based query SQL engine in Athena, it actually just looks like another table in your Redshift database. So that way you can have tables that embody your S3 data lake alongside tables that embody data that's actually stored on the Redshift cluster itself. And you can treat them as the same thing and join between them whatever you want to do. So it's really cool. It allows you to run queries against exabytes of unstructured data in S3 without the need to load that data into the Redshift cluster itself or to transform that data in any way. It provides limitless concurrency by allowing multiple queries to access the same data simultaneously in S3. It can scale out to thousands of instances if needed, so your queries will run quickly regardless of data size. And it lets you separate storage and compute capacity, allowing you to scale each independently. So with Spectrum, all of your storage is being done in S3. Spectrum is just doing the compute part of analyzing that data. Redshift Spectrum currently supports many open source data formats, including Avro, CSV, Grok, Ion, JSON, ORC, Parquet, RC file, regex serta, sequence files, text files, and TSV. So just about any common open source data format you can imagine. If you have that sitting in an S3 bucket somewhere, Redshift can parse that out and make queries against it. Spectrum also currently supports gzip and snappy compression, so if you do want to compress your S3 data to save space and save bandwidth, you can do that too. So they've pretty much thought of everything here. Going back to Redshift as a whole here, how is Redshift so fast? Well, again, it uses massively parallel processing, or MPP, to do that. Data and query loads are automatically distributed across all nodes, and adding nodes to the data warehouse is made easy and also enables fast query performance as the data warehouse grows. So it will do all of its queries in parallel, and if you need more speed or more capacity, just add more nodes to your cluster, and it will automatically take advantage of that extra capacity. It also uses columnar data storage, so your data is organized by column, as column-based systems are ideal for data warehousing and analytics, for large dataset querying, because typically you're just looking at specific columns of a large number of columns. So you can save a lot of bandwidth and a lot of lookup time by organizing your data by columns instead of by rows. The columnar data is stored sequentially on the storage media and requires far less I/O, thereby improving query performance. And by using columnar storage, each data block stores values of a single column from multiple rows. So as records enter the system, Amazon Redshift is transparently converting the data to columnar storage for each of the columns. This helps you to avoid scanning and discarding unwanted rows. Now, columnar databases are generally not well suited for OLTP, online transaction processing. So remember, an anti-pattern for Redshift is OLTP. It's meant for OLAP, like any data warehouse would be. Redshift uses a block size of 1 megabyte, which is more efficient and further reduces the number of I/O requests needed to perform any database loading or other operations that are part of a query execution. It can also do column compression. So compared to row-based data stores, columnar data stores can generally be compressed much more, as it's all sequentially stored on disk in the same type of data format. Multiple compression techniques are often applied for better results. So indexes or materialized views are not required with Redshift, and hence it uses less space compared to traditional relational database systems. It will automatically sample the data and select the most appropriate compression scheme when the data is loaded into an empty table. Compression is a column-level operation that reduces the size of the data when it is stored. Compression can conserve storage space and reduces the size of data that is read from the storage. It reduces the amount of disk I/O and therefore improves your query performance. So when you're loading data into a Redshift cluster, usually you use the copy command to do that most efficiently. That allows you to copy data into your cluster in a distributed, parallelized manner. And when you issue that copy command, it will automatically analyze and apply compression automatically. You don't have to do anything, it just does it for you. Now, it is not possible to change the compression encoding for a column after the table is created. But if you want some insight into what's going on there, it offers an analyze compression command, which will perform compression analysis and produce a report with the suggested compression encoding for the tables analyzed. Now let's talk about the specifics of Redshift's durability and scalability. Redshift replicates all of the data within the data warehouse cluster when it is loaded automatically. Also, your data is continuously backed up to S3 for you. 3 copies of the data are maintained, on the original, on a replica on compute nodes, and in a backup in S3. So your data is stored in 3 different places. There's the original copy within your cluster, there's a backup replica copy within your cluster as well, and furthermore, it does periodic backups into S3 for you. So for disaster recovery, Redshift asynchronously replicates your snapshots to S3 in another region as well. It can enable automated snapshots of the data warehouse cluster with a 1-day retention period by default. You can extend that retention period up to 35 days if you want. If you turn the retention period down to 0, however, automated backups will be turned off. Now, if you need to restore your cluster from a backup, you just choose one of the automated backups, and then AWS will provision a new data warehouse cluster and restore your data to it. You can then switch over to the newly restored cluster from the old one. Redshift replicates the data within the data warehouse cluster and continuously backs up that data to S3. It will mirror each drive's data to the other nodes within the cluster as well. Redshift will automatically detect a failed drive or node and replace it for you automatically. In the event of a drive failure, the Redshift cluster will remain available with a slight decline in performance of certain queries, while Redshift rebuilds that drive from a replica of the data on that drive, which is stored on another drive within that node. Single node clusters do not support data replication because there's nothing to replicate it to. In that case, you would have to restore your cluster from a snapshot in S3 instead. In the event of an individual node failure, Redshift will automatically detect that node failure and replace a failed node in your data warehouse cluster. Now, until that replacement node is provisioned and added to the database, the cluster will be unavailable for queries and updates. Most frequently accessed data from S3, however, is loaded first in the new node, so you can resume querying that data as quickly as possible. Single node clusters do not support data replication, and hence you will again need to restore the cluster from a snapshot in S3 in the case of a node failure on a single node cluster. AWS recommends at least 2 nodes in your cluster for production purposes. Now, in the event of a Redshift cluster availability zone outage, in this case, you will not be able to use your cluster until power and network access to the availability zone are restored because Redshift is currently limited to a single availability zone. However, you can restore the cluster from any existing snapshot to a new availability zone within the same region. So in that case too, your most frequently accessed data will be restored first from S3 so you can resume your queries as soon as possible. Again, as of now, Redshift only supports single availability zone deployments, so if an entire zone were to go down permanently, you would have to restore that data from S3 in a different availability zone. How does Redshift scale? Well, Redshift clusters support both vertical, which is increasing the node instance type, and horizontal, which is increasing the number of nodes, scaling. Your requested changes will be applied immediately when you modify your data warehouse cluster. Here's how the process works. So when you're scaling, an existing data warehouse cluster will remain available for read operations, and a new data warehouse cluster is created during scaling operations. When that new cluster is ready, the existing cluster will be temporarily unavailable while a CNAME record for the existing cluster is flipped to a point in the new data warehouse cluster. That only takes a few minutes, and it's usually done during some sort of a maintenance window. Redshift will move the data from the compute nodes in the existing data warehouse cluster in parallel to the compute nodes in the new cluster. When we discussed the Redshift architecture, we talked about how the data in your table is distributed across many compute nodes and many slices within those nodes. Now, there are several different ways of actually doing that distribution that you need to understand. So when data is loaded into a table, Redshift will distribute the table's rows to the compute nodes and slices according to the distribution style that you chose when you created the table. The 2 primary goals of data distribution are to distribute the workload uniformly among the nodes in the cluster and to minimize data movement during query execution. There are 4 different distribution styles, and they are as follows. Auto distribution. If you don't specify a distribution style, Amazon Redshift uses auto distribution, and based on the size of the table data, Redshift will assign an optimal distribution style for you. And that might be even, key, or all. So let's dive into each one of those independently. First, let's talk about even distribution. So in even distribution, regardless of the values in any particular column, the leader node distributes the rows across the slices in a round-robin fashion. So it's just going to step through each individual slice and keep assigning new data to each slice in a circular manner. This is appropriate when a table does not participate in joins or when there is not a clear choice between key distribution or all distribution. So even distribution just tries to spread things out as evenly as possible without thinking about trying to cluster data together that might be accessed at the same time. key distribution. Here, the rows are distributed according to the values in one column. So the leader node will place matching values on the same node slice. And matching values from the common columns are physically stored together. So this can come in handy if you're typically going to be doing queries based on a specific column in your data. By using key distribution, you can make sure that all the data associated with a specific key value will be physically located on the same slice, and that can speed up your queries. So the diagram here is showing you that as new rows are coming in from your incoming data, those keys will be hashed and set to a specific slice based on how that key is hashed. Then we have all distribution. And with all distribution, a copy of the entire table is distributed to every node. That ensures that every row is co-located for every join that the table participates in. The all distribution multiplies the storage required by the number of nodes in the cluster, so it takes much longer to load, update, or insert data into multiple tables. All distribution is really only appropriate for relatively slow-moving tables, that is, tables that are not updated frequently or extensively. As the cost of redistribution is low, small dimension tables do not benefit significantly from all distribution. Now, if you ever need to view the distribution style of a table, you can query the PG class info view or the SVV table info view. The reflective dist style column in PG class info will indicate the current distribution style for that table. Another important finer point of Redshift is how it uses sort keys. Sort keys are similar to indexes or indices in relational database systems. Now, while creating a table, you can define one or more of its columns as sort keys. So when data is initially loaded into an empty table, the rows are stored on disk in sorted order. This sorting enables efficient handling of range-restricted predicates. Redshift will automatically store the minimum and maximum values for each block as part of its metadata. So if a query uses a range-restricted predicate, the query processor can use the min and max values to rapidly skip over large numbers of blocks during table scans. That's why sorting is important. It allows it to skip over entire ranges of data very quickly. But how do you choose the best sort key? This is something you need to think about up front. Well, if recent data is queried most frequently, you want to specify the timestamp column as a leading column for the sort key. That will help to skip entire blocks that fall outside of the time range. So if you're querying based on recency, you probably want a time-based sort key. If you do frequent range filtering or equality filtering on one column, specify that column as a sort key. Redshift can then skip reading entire blocks of data for that column because it tracks the minimum and maximum column values stored on each block and can skip blocks that don't apply to the predicate range. If you frequently join a table, specify the join column as both the sort key and the distribution key. That would enable the query optimizer to choose a sort merge join instead of a slower hash join. Beyond that, you have the choice of a single, compound, or interleaved sort key, so let's dive into what those mean. A single sort key is just using a single column, a single value, to sort the data. Now, this is useful if you're consistently querying for data within a single filter column. For example, if you were querying primarily by date, I might choose a single column sort key by date for this data here. And it would be stored thusly, just broken down, sorted by date in order. So if I was searching only for movies that were viewed on March 19th, 2019, potentially I could skip right over all the March 18th data and go straight to that directly because date is my single column sort key. Another choice is a compound sort key. And a compound key is made up of all the columns listed in the sort key definition, in the order they are listed in. This will be most useful when a query's filter applies conditions, such as filters and joins, that use a prefix of the sort keys. Now, performance can decrease when queries depend only on secondary sort columns without referencing the primary columns. So you need to think about the order of the columns there and make sure that your primary column is one that you will most often be including in your queries. Compound is the default sort type, and they also help to improve compression. So they're a default for a reason. They're pretty general purpose, and they also improve compression as well. So if you do not specify a sort key, it will be compound. Finally, we have interleaved sort keys. An interleaved sort gives equal weight to each column or subset of columns in the sort key. This can be useful if multiple queries use different columns for filters. It uses an internal compression scheme for zone map values that enables them to better discriminate among column values that have a long common prefix. The exam is going to expect a lot of depth from you on importing and exporting data to and from your Redshift cluster. Now, the most efficient way to import data or load data into your Redshift table is using the copy command. Using the copy command, you can read from multiple data files or multiple data streams simultaneously. You can import that data in from S3, EMR, DynamoDB, or some remote host using SSH. For access control, you can use role-based or key-based access control to provide authentication for your cluster to perform those load and unload operations. So part of the copy command would be the authorization for performing that copy. For example, if you're using the copy command to load from Amazon S3, well, first of all, there's a couple of ways to do that. One is by using an Amazon S3 object prefix, in which case it would load all the data underneath a specific prefix or a path in S3. And the syntax for that would just be copy table name from S3 : / bucket name / object prefix, followed by the authorization to do that copy. You can also use a manifest file, which is a JSON formatted file sitting in S3 that lists the data files that you want to load. So the syntax in that case would just be copy table name from S3 : / bucket name / manifest file, and then again with the authorization to do that and the word manifest. So what does that authorization look like? Well, after the copy command, you would say, for example, IAM_role followed by the ARN for a given IAM role. Or if you want to do key-based authentication, you could follow your copy command with the clauses access key ID followed by your access key ID, secret access key followed by the secret access key. So every copy command says what table you're loading it into, where you're taking it from, and the authorization for performing that copy. Now, if you want to export data into S3, you would use the unload command for that. That allows you to unload or export data from your database tables to a set of files in an S3 bucket. And that's a pretty straightforward thing. But if you're being asked what's the most efficient way to dump a table in Redshift into S3, the unload command is the best way to do that, generally speaking. There's also something called enhanced VPC routing available for you, and that will force all of your copy and unload traffic between your cluster and the repositories through your Amazon VPC. Otherwise, all of that copy and unload traffic will be routed through the internet. Now, for this to work, you need to configure your VPC correctly, or the copy and unload functions will fail. So you might need to set up VPC endpoints or NAT gateways or internet gateways within your VPC to make sure that copy and unload can communicate with the repositories that you want to talk to. A little more depth on the copy command. The exam seems to be focusing on this more and more. So remember, you want to use copy to load large amounts of data from outside of Redshift into a Redshift table on your Redshift cluster. If you see a question about how do I efficiently load data into Redshift from outside, odds are the answer is the copy command. Now, if your data is already in Redshift in some other table, you don't want to use copy. Copy is for external data that's being imported into your Redshift cluster. If your data is already in another table within Redshift itself, you want to use either the insert into select statement or create table as to actually create a table that's just a view of the other table that you can refer to. So remember, create table as is what you're going to be using to refer to data that's already in Redshift in some other table. And if it's outside of Redshift, you want to use the copy command. Some neat features of the copy command: it can actually decrypt data as it's loaded from S3. So if your S3 data is encrypted, copy can decrypt it as it is loaded in. And it can do that very quickly because it has a hardware-accelerated SSL capability to keep that decryption as fast as possible. It can also speed things up by compressing the data as it's sent across. So it supports gzip, LZOP, and bzip2 compression to speed up those data transfers even further when you're using a copy command. Another neat feature of the copy command is automatic compression. This is an option that will analyze the data that's being loaded and automatically figure out the optimal compression scheme for storing it. So if you have, data that can compress very well, automatic compression can figure out how do I store this data efficiently. That is used to optimize the usage of your actual storage on your cluster. There is one special case that the documentation calls out, and I wouldn't be surprised if it shows up on the exam. If you have a narrow table, that means that you have a table that has a lot of rows but very few columns, you want to load that with a single copy transaction if at all possible. The thing is, if you have multiple copy transactions, there's a bunch of hidden metadata columns that appear, and these hidden columns, to keep track of where things left off, consume too much space. So if you're going to be loading a table that has many rows but very few columns, try to do that within one copy command. Don't break it up over several copy commands, okay? It's also important to remember that copy is designed to parallelize things and do things as efficiently as possible. So if you can do things in one copy command, why not? That's always going to work well. It's actually pretty amazing the level of depth the exam expects from you on this stuff. So let's talk about a very specific case here. Let's say that you want to copy a snapshot from Redshift automatically to another region, so you have cross-region replication of your snapshots for backup purposes. So let's say you have a KMS encrypted Redshift cluster, and you have a snapshot of that cluster being saved in some S3 region. Now you want to copy that snapshot to another region for even better backup. The way you would do that is as follows. In your destination AWS region, you create a KMS key if you don't have one already, and then you set up a snapshot copy grant, specifying a unique name for that snapshot copy grant in the destination region. As part of setting up that copy grant, you specify the KMS key ID that you're creating it for. Then back in the source AWS region, you will enable copying of snapshots to the copy grant that you just created. So by using a copy grant that you set up using a KMS key, you can securely copy KMS encrypted snapshots for your Redshift cluster across to another region. Another bit of connectivity trivia is DB-Link, and DB-Link is an extension that allows you to connect your Redshift cluster to a PostgreSQL instance, which might be hosted using Amazon's RDS service. At a high level, you might want to do that to get sort of the best of both worlds between the columnar storage of Redshift and the row-based storage of Postgres. Or you might be using it as a way to copy and sync data between a PostgreSQL instance and Redshift. So if you want a very efficient way of copying data and keeping data synchronized between Postgres and Redshift, the DB-Link extension is a way to do that. The way it works is like this. So basically you launch a Redshift cluster and you launch a PostgreSQL instance as well, in the same availability zone, mind you. You would then configure the VPC security group for the Amazon Redshift cluster to allow an incoming connection from the RDS PostgreSQL endpoint. You would then connect to the RDS PostgreSQL instance and run the SQL code you see here to establish that DB-Link connection between the PostgreSQL instance and Amazon Redshift. So just remember, DB-Link exists to connect Redshift to PostgreSQL and get the best of both worlds, or maybe to copy and synchronize data between the two more efficiently. How does Redshift integrate with other AWS services? Well, let's go through a few of them. So Amazon S3, you can use parallel processing to export your data from Amazon Redshift data to multiple data files on S3. And of course, you can also import data from S3 or even sit on top of it using Amazon Redshift. Amazon DynamoDB. So by using the copy command, you can also load a Redshift table with data from a single Amazon DynamoDB table. So it's possible to import data from DynamoDB into Redshift using the copy command as well. On EMR hosts or EC2 instances, you can import data using SSH. So again, via the copy command, you can load data from one or more remote hosts, such as EMR clusters or whatever you're running on EC2 for that matter. It also integrates with the AWS data pipeline, so you can automate the data movement and transformation in and out of Redshift tables using data pipeline. And finally, the AWS Database Migration Service, or DMS, can migrate your data into Amazon Redshift for you, or at least help you with the process. So the Database Migration Service is a whole big topic of its own. Basically, it's a set of tools that allow you to migrate data from some existing data warehouse into Amazon Redshift, and often there's a lot more to that than you might imagine. You will also need to at least know what Redshift Workload Management is, WLM for short. It's a way to help users prioritize workloads so that short, fast-running queries are not stuck behind long-running, slow queries. The way it works is by creating query queues at runtime according to service classes. And configuration parameters for various types of queues are defined by those service classes. Now you can modify the WLM configuration to create separate queues for long-running queries and for short-running queries, thereby improving system performance and user experience. You can set all this up using the Amazon Redshift Management Console, the Amazon Redshift command line interface, or the Amazon Redshift API. The topic of scaling and tuning your Redshift cluster comes up a lot in the exam as well. One feature you need to know about is called concurrency scaling. This feature allows you to automatically add cluster capacity to handle sudden increases in concurrent read queries. So if you have very bursty access to your Redshift cluster where you have these sudden floods of read queries that come in from outside, concurrency scaling can automatically scale up your cluster to handle it. It can support virtually unlimited concurrent users and queries this way. It just keeps on adding more and more capacity as needed as your read queries increase in volume. And you can use workload management queues, which we'll talk about again very shortly, to manage which queries are sent to the concurrency scaling cluster. So you can manage through what queue you assign your queries to, which ones can actually take advantage of concurrency scaling and which ones do not. This can allow you to, for example, segregate those read queries that you think might be bursty in nature or vary in time in their frequency, and use that to automatically scale out the capacity for that specific query. That kind of reduces the risk of, inadvertently adding a bunch of capacity for some offline job that doesn't really need to run fast necessarily. So you can pick and choose which queries take advantage of concurrency scaling. Obviously, it's not free, so you want to give some thought as to which queries can actually have this capability of just automatically adding more and more capacity as needed. Workload management, WLM, comes in a couple of different flavors. One is called automatic workload management. So with automatic workload management, you can define up to 8 different queues that are managed for you. And by default, you have 5 queues that have an even memory allocation between them, but you can change that obviously if you need to. So the idea is that if you have a bunch of large queries going into a queue, like big hash joins or something like that, the concurrency will be lowered on that queue automatically for you. And if you have a bunch of small queries going into a queue, like inserts or scans or simple aggregations, the concurrency level on that queue might be raised. Concurrency is just how many queries can I run at once, right? So larger queries obviously need more capacity. You want perhaps lower concurrency on those so that they get more resources, whereas small queries can get away with fewer resources and you can run more of them at once. By separating these queries into their own queues, we can take better advantage of the hardware that we have. So each automatic workload query queue can be configured in a bunch of different ways. One thing you can do is set a priority value that just defines the relative importance of queries within a workload. You can also set concurrency scaling mode. So basically that's what we talked about before with concurrency scaling. This is where you can say, I want this particular queue to have access to a concurrency scaling cluster and have the ability to automatically add more and more resources, more and more servers under the hood to handle the capacity that queue needs. That costs money, obviously, so you want to think carefully about whether or not that's enabled. You can also assign a set of user groups to a queue, and you can do that by specifying a user group name or by using wildcards. So when a member of a listed user group runs a query, that query will automatically run within the corresponding queue. So you can assign queues to query queues based on users. You can also set up a query group. All that is a label. So basically at runtime, you can assign a query group label to a series of queries, and that will define which queue that query goes into. So basically a tag, a label that's assigned to the query itself can define which queue it goes to. You can also set up query monitoring rules. These are pretty cool. They allow you to define metrics-based performance boundaries for workload management queues, and you can specify what action to take when a query goes beyond those boundaries. So, for example, you might have a queue dedicated to short-running queries, and you might have a query monitoring rule that aborts those queries if they run for more than 60 seconds. So that way you can enforce that your short query queue is actually handling short queries, and if something goes wrong with one of those queries, it's not going to hold up all the other queries in that queue. So a very useful tool there. You can also do things like kick queries off to a different queue if it violates some query monitoring rule. The other flavor of WLM is manual workload management. And by default, this comes with one queue with a concurrency level of 5. Again, concurrency level is how many queries can I run at once within this queue. In addition, there is a super user queue with a concurrency level of 1. This is a queue that's intended for administrative queries that are happening that always must run no matter what. You can define up to 8 manual queues, and you can have a concurrency level on a queue up to 50. Each of those queues allows you to define whether or not the concurrency scaling cluster is available to it, whether it can automatically, add more capacity to that queue. You can also set a manual concurrency level to that queue, defining how many queries I want to be able to run at once within it. You can assign user groups to it and query groups like we talked about before with automatic queues, just allowing you to automatically route queries to a queue based on what user is running it or what query label has been attached to the query. You can also define the memory allocated to a given queue, the timeout value for running a query within that queue, and again, any query monitoring rules that you might have. You can also enable what's called query queue hopping. So if you have a query that times out within a given queue, you can configure things to have it hop to the next queue and try it again on a different queue that might have a higher timeout or more resources available to it. One more thing to talk about here is short query acceleration, or SQA. The idea here is to automatically prioritize short-running queries over longer-running queries. The short queries will run in their own dedicated space, so they don't end up waiting in a queue behind longer queries. So this can be used in place of workload management queues if you just want to accelerate short queries. It can work with create table as statements, remember that, and also read-only queries or select statements. So these are both candidates for short query acceleration. It can automatically run those in their own space so that they don't get stuck behind longer analytic queries. And it works by using machine learning. Pretty cool. So it actually tries to predict a query's execution time using machine learning algorithms automatically. So it can kind of guess based on the query itself how long it might take and figure out whether or not that should go into the dedicated space for short queries or not. And you can configure how many seconds you consider to be short. So that's one dial that you have on short query acceleration. So remember, short query acceleration is an alternative to WLM, workload management, if all you want to do is accelerate short queries and make sure that they don't get stuck behind longer queries. And it can work with create table as statements or read-only select statements. Finally, you need to know what the vacuum command does with Redshift. Vacuum is a command used to recover space from deleted rows and to restore the sort order. So basically it cleans up your table. There are 4 different types of vacuum commands. The first one is vacuum full. This is the default vacuum operation. It will resort all of the rows and reclaim space from deleted rows. There is also vacuum delete only, which is the same as a full vacuum, except that it skips the sorting part. So it's just reclaiming deleted row space and not actually trying to resort it. You can also do a vacuum sort only, which will resort the table but not reclaim disk space. And finally, there's vacuum reindex. That's used for reinitializing interleaved indexes. Remember, we talked about the different sort keys you can have, one of them being interleaved. So reindex will reanalyze the distribution of the values in the table's sort key columns and then perform a full vacuum operation after that. And lastly, let's talk about the anti-patterns for Redshift. This also comes straight out of the AWS Big Data white paper of things they do not want you to use Redshift for. One is for small data sets, so remember Redshift's strength is that it is massive and highly scalable. If you just have a small tiny table that you want to store, RDS might be a better choice for that. OLTP, again, they cannot stress enough that Redshift is made for analytic queries, for OLAP. If you need to do transactional, very fast queries, you want to be using RDS or DynamoDB instead. And they're also listing unstructured data for me, which is kind of strange because Redshift Spectrum kind of exists to let you query unstructured data in S3. But if you do need to do some ETL, you should do that first with EMR or Glue ETL or something like that first. And it is not appropriate for storing blob data, meaning large binary files. If you do need to store large binary files in your data warehouse, it's best to just store references to those files where they reside in S3 and not the files themselves. Whew. So that's a lot about Redshift, but again, you do need a lot of depth for Redshift for the exam. It will be well worth your while to understand and remember everything in these slides. So what if concurrency scaling isn't enough and you need to actually resize your cluster on the fly? You need to add more capacity to it. Well, there's a few ways of doing that, and you need to understand the difference between them. So one is called elastic resize. You can use this to quickly add or remove nodes of the same type. So if you're happy with the type of nodes, the type of EC2 instances that are running your Redshift cluster, you can add more or remove them using elastic resize. With elastic resize, your cluster will only be down for a few minutes while it adds that capacity, and it tries to actually keep those connections open across the downtime as well. So you might not even drop any queries. It might not just keep that connection held open and let it resume once that added capacity is in place on your cluster. Now, one limit of elastic resize is that for certain DC2 and RA3 node types, you're limited to either doubling or halving the size of that cluster. You don't really need to remember what the specific types are for the exam, but for certain types, that is what you need to do. You can only double or halve them. If you need to do something a little bit more involved, then you need to go back to what's called classic resize, and that allows you to actually change the node types and or the number of nodes. The thing with classic resize is that if you're actually changing the node types, it could take hours or even days for your cluster to become writable again. So your cluster will be in a read-only state for the entire period of time that it takes to provision that new hardware and swap it out in your cluster. That can be a very lengthy experience. So you want to use elastic resize when you can, but if you need to change your node type, you have to use classic resize. That's the main difference there. One technique for dealing with things in that classic resize scenario is to use what's called snapshot restore resize. And this is a strategy for keeping your cluster available during a classic resize operation. So if you do need to change your node type, or you need to add a amount of capacity that Elastic Resize won't allow you to do, what you can do is use a snapshot command to make a copy of your cluster, and then resize that new cluster. So your data is still going to the old cluster while your new cluster is being resized and going through the classic resize process. Once your new cluster is finally done, you can then shift your traffic to that new cluster that's been created. So snapshot, restore, then resize is a way of migrating from one cluster to another using classic resize to minimize downtime. Some new features in Redshift for 2020. These aren't appearing on the exam as of this recording, but I imagine they will at some point in the future. One new thing that they offer is RA3 nodes, and these come with managed storage. So the thing about RA3 nodes is that they enable you to scale compute capacity and storage capacity independently. So if you have a lot of complex queries running that take a lot of CPU time, but your storage isn't necessarily that big, you can use RA3 nodes to add more computational resources to your cluster without necessarily adding more storage resources at the same time. So sometimes you need to scale those things independently. Also, a new feature is Redshift Data Lake Export. What it does is allow you to unload your Redshift queries into S3 in Apache Parquet format. And Parquet is important because it's up to 2 times faster to unload, and it consumes up to 6 times less storage. Parquet format is also compatible with Redshift Spectrum, Athena, Elastic MapReduce, and SageMaker, so it makes a lot of sense to use this when you can. It's also automatically partitioned, so if your data is partitioned by date or whatever it is, it can preserve that partitioning as it exports your query to S3 in Parquet format. Let's discuss some of the newer features in Redshift that have come out in the more recent years. 2020, I think it was, or end of 2019, RA3 nodes were introduced. This is a special node type that's optimized for Redshift. So that was kind of a big deal, and they've been building more and more on top of that over the years. The big idea here, though, is that it comes with managed storage. So they have decoupled compute and storage capabilities with the RA3 node. Basically, their observation was that storage capabilities and computing capabilities were evolving at different rates. So by having the ability to independently scale computing and storage capacity, that lets you make better use of the resources that you have for your Redshift cluster. So that's kind of a big deal. Another thing that came out in 2020, 2020, was Redshift Data Lake Export. And the idea there is that you can dump a Redshift query right into S3 in Apache Parquet format. So if you have a big query on a big data warehouse in Redshift, you can dump that out to a data lake just sitting in S3 pretty easily using Data Lake Export. The motivation of doing that is that the Parquet format is twice as fast to unload, and it also consumes up to 6x less storage. So it's a very fast and compact way of exporting data to a data lake. And that data lake that you end up with will be compatible with Redshift Spectrum, Athena, EMR, or SageMaker, anything that can read from S3. It's also automatically partitioned for you, so you don't necessarily have to think about that. Also, more recently, in 2022 or end of 2021, they've introduced spatial data types. So now there are geometry and geography data types available in Redshift. So if you do need to do things with mapping, those sorts of applications, you can do that in Redshift now with those new data types. And also a new feature is cross-region data sharing, new for 2022. It's sort of been evolving over time, but it's really evolving more lately. The idea here is that you can share live data across Redshift clusters without having to copy them. So we talked a lot about replicating data across different regions and different entities and how much of a pain that can be. So with cross-region data sharing, they've really strove to simplify that as much as possible. So that allows you, again, to share live data across regions. That's a new thing. And even across accounts if you want to, in a secure manner, very easily. To do that, you do need to use that new RA3 node type that we talked about. It's only supported on our RA3 node types. So that's a big deal. Cross-region data sharing, new easy way of managing that problem. Also, something relatively new, 2021, I think this was introduced. It's something called Aqua. That stands for Advanced Query Accelerator. And it's this layer that sits between S3 and your Redshift cluster. So if your data is stored on S3 under the hood, Aqua will accelerate the processing of that data by doing it closer to where the data is. This is only available on RA3.4XL and RA3.16XL node types. So again, important to use that RA3 node type on Redshift clusters now if you want all the latest and greatest features. The idea is that it's pushing reduction and aggregation queries in particular closer to the data. So that Aqua layer is sitting closer to the S3 servers, and it actually has a special high bandwidth connection to S3 to make it even faster. How much faster is it? Up to 10 times faster, they say, and at no extra cost and with no changes to your code. Pretty good deal. And like I said, it's got a special high bandwidth connection to make it even faster. All you have to do is turn it on. So when you're configuring your cluster, if you chose those correct node types, you will see an option when you're configuring your cluster to have Aqua on or off. Turn it on. Why not? It's free and it's faster. All it can do is any good. So that's what Aqua is all about. Redshift continues to be a source of heavy innovation in AWS, so watch this space. We'll be updating these lectures as time goes on as they add more and more capabilities to Redshift. It's an exciting place to be. So a couple of specific security concerns I want to talk about with Redshift. We'll talk about security a lot more later in the course, but here are a few things that might show up on the exam. One is the issue of using a hardware security module or an HSM with Redshift. And if you're using an HSM with Redshift, you need to use a client and a server certificate to configure a trusted connection between Redshift and the HSM. Now, if you're trying to do this after the fact, you're trying to add an HSM to an existing Redshift cluster, you're going to have to copy it over. So if you want to migrate an unencrypted cluster to an HSM encrypted cluster, you're going to have to create the new encrypted cluster first and then move your data over to that encrypted cluster. Okay, so that's kind of the nitty-gritty of using an HSM with Redshift. You need a client and server certificate to do it. Also, there's a cool thing where you can use grant or revoke commands in SQL to actually define access privileges for individual users or for groups of users in Redshift. So an easy way to manage permissions in Redshift is to just say something like grant select on table foo to Bob. That would grant the permission to Bob to do select statements on the table named foo. And you can do things like grant all or grant drop to let people drop data as well. This can all be managed individually to a user or group just using the grant command, just like any other SQL command, or the revoke command if you want to take those permissions away. So that's the fundamental way that you manage security and access permissions in Redshift. So a pretty recent development, just like EMR is going serverless, so is Redshift. Redshift Serverless is now available as well, and this promises to automatically scale and provision your Redshift cluster for your workload. So again, you don't have to think about how much capacity you need. It will figure it out for you. The idea is to optimize your costs and performance. So since you're only paying for the capacity that you're actually using, that should save you some money. And it will also optimize your performance, because if you are going to run a very demanding query of some sort, it can automatically scale that up for you without you having to think about it, which makes life a lot easier. Under the hood, it's using some sort of fancy machine learning. They don't go into details about it, but ML to maintain performance across what might be a variable and sporadic workload. So even if you're hitting it with ad hoc queries, it will learn how to deal with that. The main purpose of this, though, is to make it really easy to spin up a Redshift cluster, right? So I don't have to think about capacity anymore. I can just go ahead and spin up Redshift, and it will automatically figure out the capacity that I need, and that's all I get billed for, which is great. So if I want to spin up a little development environment or a test environment, I can do that in one little page here. Just go ahead and set up my new database, and it will automatically just give me the capacity that I need and no more, which is a lot easier. If I want to do just a quick ad hoc business analysis thing, spin up a quick cluster, answer a question, get out, can do that too. Don't have to think about it too much. They've just made it a lot easier to set up your cluster. So that makes it easier for other people to use it and encourages you to use it for more types of applications. Once you have spun it up, you just get back a serverless endpoint of some sort, and you also get a URL for connecting to it through JDBC or ODBC. Or if you're just doing a quick ad hoc thing, you can just use the query editor in the console as well, like we've seen before. You don't have to connect to it externally if you don't want to. So getting started, the only hard part right now is actually setting up the IAM role needed to set up Redshift Serverless. So you need to start off by creating an IAM role by hand that has this policy attached to it to the right here. You need to make sure that you have access to the Redshift Serverless action by hand. And I'm sure they'll make that easier eventually, but for now, you do need to set that IAM role up yourself. Once you have that, though, when you're setting up your new Redshift Serverless cluster, all you need to do is tell it what your database name is, the user credentials for your admin user, which VPC you want to be running within, any custom encryption settings you might want to use. By default, it's just going to use an AWS-owned KMS key, which is usually fine, and any special settings that you might want for audit logging. But that's it. You just fill out one page of that information, and you have a Redshift serverless cluster waiting for you to use it, which is kind of awesome. After the fact, you can manage snapshots and recovery points later on after you've created it. Those are all still supported as well. So you can have periodic snapshots of your data and the ability to roll stuff back, from the previous day or whatever using recovery points later on. That's all still there. Let's talk more about how resource scaling actually works in Redshift serverless. So because we're shifting our thinking to serverless, they can't really bill us in terms of servers anymore if they're not really exposing what those servers are. So instead, they're going to have us think about what they call Redshift processing units, or RPUs, and that's their new billing metric. So you pay for RPU hours down to the per second level, plus any storage that you're using. So the billing in Redshift serverless is based on how many Redshift processing units you're using per hour, plus any associated storage fees. So that's charged, per gigabyte over time units. You can specify your base RPUs. So kind of like you could specify initial capacity with EMR serverless, same idea with Redshift serverless. You can adjust your base capacity. Now by default, it will be set to automatic, so you don't have to think about it at all. But if you do want to improve your query performance and you know that you're going to need a little bit more capacity for that out of the gate, you can give it a hint. You can say that I want between 32 and 512 RPUs as my base level in my serverless cluster to start with. I can also set my maximum RPUs. So if I want to make sure that I never go beyond a certain resource consumption to control my costs, you can do that too. Of course, they want you to use it to increase your throughput. So although in practice, you probably want to use max RPUs to ensure that you're not billed for more than you expect, you can also use it to improve the throughput of a job if you think the maximum RPUs is set too low. A few more things about Redshift serverless. So basically it does everything that Redshift can, with a few exceptions. One is that Redshift Spectrum is currently not supported under Redshift serverless. I have a feeling that will change at some point though, because there is some documentation about how that's built. Parameter groups are not supported with Redshift serverless. Workload management also doesn't work with it. Wouldn't make much sense if it did, right? The whole point is that you don't have to think about that too much. AWS partner integration, currently not supported with Redshift serverless. And also maintenance windows and version tracks are not supported with Redshift serverless. That's a little bit, that one's worth talking about a little bit. With normal Redshift, you have these maintenance windows, so you kind of know when updates are going to be applied to your cluster and you can plan accordingly. With Redshift serverless, if a software update is being rolled out to Redshift itself, you will get your connections dropped without any warning. So there's no real advanced planning for that with Redshift serverless. That might be something to think about when you're deciding whether or not to use this for now. Also, there are no public endpoints with Redshift serverless. You must access it within a VPC. It will not make that accessible publicly yet. That might change. Monitoring is something they talk about in the documentation for Redshift serverless. That did also change a bit. So there are a bunch of different views that it provides for monitoring purposes, like sys query history, sys load history, sys serverless usage, and a few more. They do what you think they do. So basically it's a history of the queries. There's also a query detail view if you want more information, historical information about the load on your serverless cluster, the usage of that cluster. This can all be useful in sort of troubleshooting performance issues. Maybe you need to include, maybe your maximum RPUs is set too low, for example, and that might be a way to figure that out. Also, it publishes data to CloudWatch. Connection and user logs are enabled by default. There's also optional user activity log data if you want to publish that as well. That will be published under the AWS Redshift Serverless CloudWatch topic. Metrics that are published in CloudWatch include queries completed per second, query duration, queries running, stuff like that. And you can break that down by various dimensions, such as the database name, the latency, which is split up into short, medium, or long, the query type, and the stage of the query. The stage that the query is in as it completes. So that's all available to you as well. But in a nutshell, Redshift serverless pretty much works the same way as Redshift. The only difference is that you're not thinking about the underlying capacity, the underlying servers. It's doing that for you. So instead of being billed by server usage explicitly, you're being billed by RPUs. And you have a few ways of controlling that if you need to, including the base and maximum RPU capacity for Redshift serverless. So let's continue building out our data warehousing requirements here for Cadabra.com. This time we're going to use Amazon Redshift instead of Athena, and that's a managed solution that requires you to spin up a cluster with a fixed number of servers. So a little bit more work, a little bit more thinking you have to do about capacity there, but at the end of the day, it's going to operate very similarly. Now, just to tie things together even more and mix things up a little bit, I'm actually going to use Amazon's Redshift Spectrum to access our data in S3, because while I could copy that data into Redshift directly and just have it sit within our Redshift servers, why have a copy of the data if you don't need to? Since I already have AWS Glue in place, that can expose my S3 data to Redshift Spectrum, and I can just query that data directly, kind of like I did with Athena. But the advantage is that if I had other tables that were loaded into Redshift, I could join that S3 data with that other data as well if I wanted to. So that's the main difference there. So let's dive in and build this out. So let's get started with our hands-on lab here. I'm back in my AWS management console here. And what we're going to do, just to recap again, we're going to create a Redshift cluster, a very cheap and small one, and actually use Redshift Spectrum to go through AWS Glue to talk to data in our S3 bucket and query that directly from our Redshift cluster. So let's get started. Start by going to Redshift. So go ahead and just type in Redshift in the handy search bar here and select that. And there is a new UI here as of December 2019, so we're going to go ahead and use that because that is the way of the future. They have made it a whole lot simpler. This used to be a lot more complicated to create a Redshift cluster, and they've really simplified it quite a bit. So we can just click on this big friendly Create Cluster button. And we definitely don't want the $13 an hour version here. We're just going to be querying a very small table that lives in S3. We don't even need to store anything locally at all here. It's going to be querying directly to S3 using Redshift Spectrum and AWS Glue. So to save some money, I'm going to not choose the $13 per hour option. I'm going to choose the 25 cent per hour option here, a DC2.large instance type. And I don't even need two of them. One of them will be plenty. So we'll have a cluster of one, if you will. And you can see here that that should be reasonable. We're going to shut this down as soon as we're done, so it's not going to cost that much money. We need to give it a name. Let's call it Cadabra. Note the database port of 5439. If you were going to connect to this database externally, you would need to remember that number. We'll stick with the default username, AWS user. And you will need to give it a password, so type in whatever your favorite password is and remember it. And the next step is the cluster permissions. And although it says it's optional, we do need it because we need to make sure that our new Redshift cluster has the necessary permissions to talk to our Glue catalog and to S3 to get at the underlying data. By default, it will not. So we're going to have to create a new IAM role for this. So let's break out into a new tab here. I'll just right-click on the AWS logo there, open in a new tab, and we'll head on over to IAM to create the role that we need. So let's go to Roles, and then Create Role. And this will be an AWS service. We're creating a role for Amazon Redshift, and the service in question is Redshift, so we'll select that. And our use case is Redshift Customizable. And then we'll go to the next step, give it the specific permissions that we want. Let's go ahead and search for the two that we need to give it. One is Amazon S3 read-only access should do. We just need to read the data in S3 for this query from Redshift. Select that. And we also need to give it access to Glue. So I'm going to give it broader access to AWS Glue. Glue console full access should be sufficient there. More than sufficient, actually. All right, moving on, we'll go to tags. We don't need to give any tags to this role. And go on to the review stage. Double check that we have those two policies attached to it. We need to give this role a name. Let's call it Redshift Spectrum. And create role. All right, let's find that role we just made. Click on it. And copy the ARN. We're going to need that. So click the copy icon there and keep that in your clipboard. Now back to the Redshift console, we can go to Cluster Permissions and open that up. And now if we refresh this, we should see in the list our new Redshift Spectrum role. So go ahead and attach that. Click on Add IAM Role. It's not enough to just select it. You need to hit that button as well. And here's where things get a lot easier than they used to be. There's some handy default settings here for all the network and security and backup settings and everything here that you can just use. Now, assuming your account was created sometime within the last few years, you should have a default VPC that you can just use for this cluster. If you do need to create one, then you're going to have to go off and actually create a new subnet and create a VPC from that and assign that to your Redshift cluster here. But we can explore what the options are here by just temporarily saying don't use defaults. So you can see you can specify a specific VPC if you want to, not just use the default one, and a specific subnet group, a specific availability zone as well. These are all things you can set if you need to. Database configurations. Interesting that they kind of hid that there. It's kind of important to know what your database name is, right? So remember, dev is going to be the default database name. If you did want to create a different database name initially, you would specify that here. Encryption, also very important to note that you can do that. This comes up on the exam a lot. So you do have options here for encrypting your data on the cluster at rest using AWS KMS, or a hardware security module as well, using Amazon HSM. And the new console has this annoying habit of refreshing itself when you least expect it. So maintenance, let's take a look at what's in there. Okay, fine. This is just saying that we're going to allow it to keep up to date on the latest approved cluster version when it goes down for maintenance. We have monitoring options as well with CloudWatch. I'm not going to have any CloudWatch alarms here set up, but you could create them here. Again, this comes up on the exam quite a bit. CloudWatch is there for monitoring your logs and making sure that things are working as expected and alarming if they are not. So you could set that up there as well. You can also have automatic backups with an automated snapshot schedule too. And you can specify how often you want those snapshots to run and how long they should be retained for. But I just want the default settings. And there it goes, reconfiguring everything again. Let's scroll back down here and go back to use defaults for additional configurations. Double check everything is still correct here, because with all those refreshes, it is not. Yeah, they got to fix that, guys. Let's change that identifier name back to Cadabra and put our password back in. All right, double check everything before it refreshes again. So again, just make sure that we're using the cheap one, the DC2.large for 25 cents an hour. We have a single node. We're going to name our cluster Cadabra. It's running on port 5439. Our master username is AWS user. The password is whatever you set. And we have set our IAM role. Oh, we have to attach that again too. Redshift Spectrum. Add IAM role. And we're going to use defaults for everything else. So before it goes and refreshes everything yet again, let's hit that Create Cluster button. And now we just have to sit around and wait for it to get out of modifying state and wait for it to be available. So we're going to hang out for 5 or 10 minutes here, and I'll come back when it's done. All right, a few minutes have passed, and our cluster is now in available status. So let's go ahead and select that Cadabra cluster we just made. And you can see it's up and running. Everything looks healthy. Let's go ahead and click on the Editor tab here, and that will allow us to actually interactively query this new database. Once you've selected that database, you'll need to sign into it. And now it's actually remembered that I've signed into this before. So for you're going to have to type in that you want to connect to the dev database with the AWS username and whatever password you specified back when you created this cluster. So go ahead and connect to that database. And here we are. So go ahead and click on the Editor tab here if you haven't already. And what we need to do is create an external schema to actually connect our Redshift cluster with our S3 data through the glue schema that we created for it to make it look like a database table. So rather than actually importing a copy of that data from S3 into the cluster itself, we're going to use Redshift Spectrum to actually query that in place on S3 using the schema that we created using glue. So to do that, we need to create that external schema first. Type in the following to take care of that. Let's say create external schema, order log underscore schema is what we'll call it, from data catalog. So this is going to import it from the glue data catalog. That's what that means. We're going to look for the database in the glue data catalog called order logs with the following IAM role, single quote, and hopefully that's still in your clipboard. That's the role that we created earlier in this exercise. And region with single quote, whoops, whatever your region name is. For me, that's US-East-1. All right, let's hit Run Query to take care of that. And it's completed. So let's refresh our data objects here. And we should now see our order log schema. Let's select that. And sure enough, there's our table. So take note of what that table name is for you. It might be something different based on how you imported things earlier. For me, it's orderlogs_sundog_edu. And go ahead and click on that and you can explore what's in it. Sure enough, there's a schema for our order information from that order data set that we imported into S3 earlier in the course. Pretty cool. So now we can treat that just like any other database table. Let's run a query against it, shall we? Let's hit clear and start typing the following query. Let's say select description, comma, count star, like that, from, and to specify the table name in this manner, we need to give the schema name dot the table name to actually connect it up properly. So the schema name is order log underscore schema, and the table name will say dot order logs underscore sundog edu. Again, substitute whatever the table name is for you. All right, so we know what we're selecting from. Let's say what we're going to extract here. We're going to look for things that have a where country equals single quote France. So we're going to look for orders from France and for a specific time frame. So we'll say year equals, and substitute here whatever year you actually imported your data into. You might have to go and refer back to your S3 bucket to figure out what that is. For me, it's going to be way back in 2019, and a month equals 02. That's way back when I first created this very first version of this exercise. For you, obviously, it will be a much more recent date. But yeah, substitute whatever month you're taking this course in, basically, and that should do the job. And we will say group by description. And that's it. So let's break down this SQL query here. It's nothing too fancy. We're just saying that we want to count up how many times each individual product description occurs, where the order came from France, and it was in the specific year and month that we're giving here. So let's run it and see what happens. Looks like it's doing something. And there we have it. Very cool. We have some results here. So the order and things that are returned might be different for you, but you should see a similar output to this. So, for example, from France, we had 28 orders of Woodland Charlotte bags and 22 orders of a gumball coat rack and 15 of a robot birthday card. So cool, it worked. We actually set up a new Redshift cluster from scratch, a very simple one, using a very inexpensive node instance type and only one of them. And rather than just importing data into the cluster itself, we actually connected it to our data that's sitting in our S3 data lake using Glue Data Catalog and S3 and a specific IAM role that allows everything to talk to each other. So we're using Redshift Spectrum to actually look at that information that's being stored in S3 in our data lake and interpret that as yet another database table. Pretty cool stuff. All right, that's it. Now remember, this is up and running, and we are being charged 25 cents per hour for the hardware that we're using here. So if you are going to go away from this course for a while, you probably want to shut that down. You can go back to the Clusters tab here and select that node, and from the actions, you can say delete if you want to actually delete that cluster and make sure that you won't be billed for it any further. However, our next exercise, when we use QuickSight, does build upon this Redshift cluster. So if you do intend to move forward with this course soon, go ahead and leave it up. But just remember not to leave it up forever, or else you're going to have a very nasty surprise at the end of the month. Remember, when we created this cluster, it said it was going to cost us at least $180 per month if you just let it run the whole time. So do remember to shut this down when you're done with it, guys. Otherwise, you're going to have a pretty big bill at the end of the month that you didn't anticipate. So you have been warned. Make sure you delete this thing when you're done with it. And with that, let's move on. Let's talk briefly about Amazon RDS, the Relational Database Service. It's not really relevant to big data. It's really more for small data, but it will come up on the exam and you need to know what it is. Usually sort of an example of what not to do, or maybe an example of how to import your RDS data into a larger big data system. What is RDS? Well, it is a hosted relational database, and that can be any of the following database types. Amazon Aurora, which we'll talk about shortly. You can also host a MySQL database, a PostgreSQL database, MariaDB, which is basically an open source version of MySQL, Oracle, or Microsoft SQL Server. So it's a way to just have AWS host your own little database host so you don't have to worry about maintaining that database host yourself, which, as we all know, being a DBA is not always a fun thing, kind of a handy thing. But it's not for big data. Like I said, it might appear in the exam as an example of what not to use for a big data problem, or in the context of migrating from RDS into Redshift or something like that. It's made for smaller needs, where you can get away with a single database host and store all of your data in there. For example, I use RDS in Amazon Aurora for backing up my websites. So for WordPress, it's using RDS as its backing store for that. A good time as any to talk about ACID compliance. This comes up frequently in the world of relational databases in general, and all of the RDS databases offer full ACID compliance. So, if you do need a database that meets these requirements, RDS can be a solution, provided that you don't need massive data sets that can't fit on a single host. Now, under the hood, it might actually be using more than one host. That's all kind of a black box to us, but it still makes sense to think of RDS as more of a small data solution. ACID, anyway, stands for Atomic, Consistent, Isolated, and Durable. And just a little refresher here for you guys. So atomicity ensures that either the transaction as a whole is successfully executed, or if part of a transaction fails, then the entire transaction is invalidated. So if you're sending a transaction that does more than one thing, if any bit of that fails, the entire transaction gets discarded. Consistency ensures that the data written to the database as part of the transaction must adhere to all defined rules and restrictions, including constraints, cascades, and triggers. Isolation ensures that each transaction is independent unto itself, and this is critical in achieving concurrency control. Finally, durability ensures that all of the changes made to the database be permanent once a transaction is successfully completed. Let's talk specifically about Amazon Aurora, which is one of the options for RDS as one of the database types you can use. Amazon Aurora is compatible with both MySQL and PostgreSQL, so if you have a need for a MySQL or a PostgreSQL backend for something, Amazon Aurora can slip in there and take its place. Again, I'm using this, for example, as a backing store for my WordPress websites. And it is up to 5 times faster than MySQL and 3 times faster than PostgreSQL, which is pretty darn impressive. And as far as cost goes, it's up to 1/10 of the cost of hosting your own commercial database. Each Amazon Aurora instance can have up to 64 terabytes of storage and up to 15 read replicas, so it actually does scale up pretty far. It can continuously back up to S3 for you, have replication across availability zones, and it can automatically scale now with a new feature called Aurora Serverless. So Aurora is sort of evolving beyond the small data world and into the big data world now, so it'll be interesting to see where that goes over time. But it's kind of hard to imagine why you wouldn't use Aurora if you're in a situation where you would normally use MySQL or PostgreSQL. As far as security goes with Aurora, it offers VPC network isolation, obviously. It can also do at-rest encryption using KMS, so data, backup, snapshots, and replicas can all be encrypted. And it can do in-transit security as well using SSL. So that's Aurora in a nutshell and RDS. Again, usually not in the context of big data, but Aurora is going in interesting directions, so we'll keep an eye on that going forward.